Actually, yeah, but people survived that. People were around for a million years before
Hello, everyone. Thank you so much for coming today to AIAA Los Angeles, Las Vegas. Los Angeles section Planetary Defense Mini Conference. Sorry, our section name has been changed to Los Angeles section officially. We used to be called Los Angeles Las Vegas section since 2012. Sorry for folks online. I know you have been waiting since 10:25 or earlier. We have been trying to figure out some internet issue, but now it's all resolved. So sorry for waiting. So we will now start the program. So my name is Ken. I'm the events program chair. Before we start the program, turn to the hand to Dr. Nahum Melamed. I want to say a few words about logistics. For folks here, if you park in the Civic Center, across street, community center, please move away. Please move it to the library parking, because if you park in the Civic Community Center across the City Hall, they will close the gate at some point. There's no way you can get out, and you'll get tickets. And the library parking here in this direction behind the library is free for a whole day. During the library hours. So please move your car. We are not responsible for your parking. The other thing is, if you need any food, lunch. So we have a 15-minute lunch break. So if you need food, sorry, this time we didn't prepare the food for you to order or bring some refreshment, because this is the transition of the fiscal year. In the future, we'll get more funding for you. There's a corner burger just across the street, just like 1 minute walking. You can get hamburger, drinks, coffee, smoothie, Coke, everything you want, and it's just across the street. So the restroom is just right outside the door of this meeting room, but you need to wave hands to the front desk because it typically is locked. Also, the badges is on the back in the check-in table, so please get your badges. And if you need anything, please raise hand and let us know. The membership, if you are a member, thank you so much. If you are not a member yet, please look at the membership brochure or look up to aiaa.org/join and join online. If any question, please let me know. So that's thank you so much again. So this meeting has been recorded. So for the speaker, most of them has agreed, gave us the permission to record, and the link for the recording will be posted online probably tomorrow after processing. So thank you very much again. So let us welcome Dr. Nahum Melamed from Aerospace Corporation. He's event lead today and moderator. Thank you so much, Dr. Melamed.
Thank you very much, and welcome to the Asteroid Day event of 2024. So, for those that are not aware, we are commemorating an event that occurred over 100 years ago over Siberia in Russia, where an asteroid exploded in the Siberian atmosphere and exploded. Destroyed about 2,000 square kilometers of Siberian forest, and most of the big cities of the world are smaller than the area that was instantly destroyed. And so that creates a concern. It's a very, very low likelihood event, but it is possible that a major city could be hit by an object like this and get destroyed instantly. So the Asteroid Day organization was founded, I think, about 10, 12 years ago, an international advocacy organization for promoting activity related to planetary defense. And I have been involved with this topic for about 20 years now through my organization, Aerospace Corporation. We've been doing studies, we've been doing workshops, we've been organizing conferences. Time permitting, at the end of the agenda today, I can show what some other activities that we do. But I will start with a study that we've done recently to address a very, very interesting worldwide event that will occur 5 years from now, and that is called the passage of asteroid Apophis very close to the Earth. Any of you have not heard about asteroid Apophis? You have, yes? So all of you have heard about this event? Oh, okay. Thank you. So asteroid Apophis is a significant asteroid. It's about 340 meters in size. It's going to zip by our planet on April 13 of 2029. It's going to come below the geosynchronous satellites for a few hours. And so that's an opportunity to take measurements for science mainly, to measure the effect of the gravitational attraction on the object. We don't know what it's made out of, but it is made out of rubble pile, pieces of rocks that assemble together. They could be dispersed, there could be some fragments being ejected off, or there could be changing in its shape. So there is a lot of interest in getting measurements of the object before, during, and after the close approach. I'm going to show a quick proposal that we have put out that would generate both science value, scientific measurement value, and some values for what is called space situational awareness through the capabilities that Aerospace Corporation has. And so with that, I will start with a presentation that we put together for several organizations. And let's start with moving into the next slide. Looks like this is not responding.
1 second.
And maybe you can just move into the next slide. Excellent. All right. So okay. This is a quick overview of a much bigger set of presentations that we put together. I created an abridged version for today, just to show the gist of what we are doing. And first, I described Apophis. It's an asteroid that's going to zip by our planet. Oh, it's working. Fantastic. Thank you. Oh, you can pinpoint with it. All right. So yeah, so this is the asteroid. And what is it being proposed? So we would like to propose to leverage the passage of Apophis around the planet to be served as sort of like a bad actor, right? Bad actor meaning an object that we are not aware of, but we would like to know more about it, approaching our planet. And we are going to train our systems to detect Apophis and try to characterize the object in order to have awareness of what's going on around the XGO region. XGO is the region between the geosynchronous orbit and the moon, which is a new frontier for us to be aware of. So we would like to develop capabilities to become aware of what's going on there for many purposes. But the focus here is mostly for scientific. And so what you see here is an animation of the passage of Apophis around our planet. You can see that the gravitational attraction of the Earth will bend its orbit significantly. And that's going to possibly cause a modification of its shape. We would really like to see how it looks before, during, and after these very few hours of passing very close to our planet. This is the main objective of our mission proposal.
Dr. Melamed, are you good taking questions as we go, or should we wait till?
I think so, yeah.
Okay. All right, Dr. Melamed. I'm Rick Garcia, U.S. Space Force here at LA Air Force Base. So thank you for highlighting that detail where we're going to have that bend in the curve, right? So are we seeing any possible disruptions in space weather and some of the comms over satellites that are in LEO, GEO, or MEO that we might expect as a result of this asteroid body or are we even kind of testing for that or being aware that might be a possibility on space weather side, or maybe even with comms, right? Or comms.
We anticipate no disruption to space weather and to COM. It's not going to be affecting any of those phenomena. The only area of possible concern that we have is that if pieces might be shed off the object while it's doing the close approach and start to travel around the geosynchronous region, there is a possibility, a very small possibility, they might collide with one of our assets there and potentially disrupt its functioning. Even if it's going to collide with a non-functioning object, it could create space debris in this region, which is a concern. I don't know if anybody has done any calculations of the likelihood of anything like this happening, but we estimate the likelihood is very small, but not zero. Nothing related to space weather or anything else. No effect to that, or communication.
Okay, thank you.
Mark.
Yeah, can I ask a simple question, Mark Henley? A lot of these asteroids just seem to have small moons around them. Okay, and I don't know if it's 15% or what the number is, but some significant fractions. And if this one happens to have some other small moon, that could also be disrupted and might be an impact risk. And
Yeah.
you were saying if other parts somehow fly off the surface, but that anything in orbit around it could more easily be separated.
That's correct. So to my awareness, it's not a binary system as far as I'm aware of. Otherwise, it would have been, advertised in the news.
Yeah.
But there is a possibility that pieces would be shared and it could become binary or multiple system if pieces would start detaching from the main body and circling around.
Yeah.
We would like to take those pictures, right? This is something we'd like to be aware of, but I don't think that it's a binary system per se, like with the two sizable objects orbiting each other.
So you say that, there might be a little stronger gravity there, like comets have been disrupted as they get stretched by tidal forces, right? So
Yes.
I don't know if that's an issue or not.
Yeah, I have not heard that this is a major concern. The only thing is that if pieces are detached during the flyby and fly towards geosynchronous assets, perhaps there is a small concern that would be an issue. Obviously, dealing with space debris in the geosynchronous region is a problematic topic because there is no way to clean this. It's not a low Earth orbit where some of those space debris enter. This is a problem, right? So, but let's thank you. Let's keep those questions to later because I want to show what we are proposing to do. But these are good questions. So that's the basic proposal. One of the aspects of our proposal is that we think that it can support the OSIRIS Apex mission. OSIRIS Apex mission, I will present it in a moment, is a mission that is funded by NASA to rendezvous with asteroid Apophis. It is a mission that was intended originally to bring a sample from asteroid Bennu, which was a successful mission. It brought a sample, it's being investigated now, and the spacecraft itself is in good shape, so they repurposed the spacecraft to rendezvous with Apophis in 2029. But because the amount of Delta V that is available for this mission is inadequate to do a rendezvous before the close approach, it's going to do the rendezvous after the close approach, and it's not going to be able to see the details that occur during the few hours of the flyby. And so our concept is intended to close this gap and present some scientific measurements during the few hours of the very close approach. And this is how it looks. So you can see here that the OSIRIS-REx, which successfully picked samples from Bennu and brought it back to the Earth, is going to be very, very far, thousands of kilometers from Apophis at the time of the close approach, which is exactly around this date here. Plus, it's not going to be very well illuminated by the sun to be able to measure the shape of the asteroid from ground telescopes. So ground telescopes will not be optimal in terms of detecting any changes to the state of Apophis. and it's going to be very far. We are hoping that we can put a satellite, maybe a CubeSat or something similar to that, at just a few kilometers from Apophis, and use a high-resolution camera to take detailed pictures before, during, and after. That's going to be amazing. It cannot be done from 10,000 kilometers away. And so what we're proposing is to create some sort of integrated campaign in which we will put a aerospace build one or more satellites right at the time of the close approach. And about a week later, when Osiris Apex will converge into a rendezvous, trajectory with Apophis, we will inform the Osiris Apex with the information that we have collected during the close approach with our system. There are several goals that we are trying to address. This is just a few of them that were published in this report, which everybody is welcome to download. It's publicly available. And this is the first three goals are of interest to the community in terms of, enhancing NEO detection. NEO is the terminology for near-Earth objects. These are asteroids and comets that come close to our planet. To enhance the capability to detect and track those objects and characterize them, improve their modeling and prediction, and develop technologies for reconnaissance. All of these fall within our mission concept to be able to detect objects that are in near-Earth space. Additionally, the US Space Force also issued some goals, and goal number 3 seems to fit our concept as well in terms of creating a space situation capability, awareness capability. So our mission design is intended to address both these set of goals for science and for national security. The sequence will look roughly like that. So there's going to be a detection of an object, issuing an alert to the relevant organizations. It will be followed by characterizing the object by whatever means are available to us. And if we determine there is an element of risk, then we're going to decide on some action. That's a typical process that is done with every common situation. So that's going to be employed by or utilized by our mission concept. We are considering several small satellites, several form factors. And this is an example of one form factor that was considered for this mission. It's called a disk sat, simply because it has the shape of a disk. It's a new invention by aerospace from the last few years. It has several advantages over the usual CubeSat because it has a very large surface area, and it can the volume is equivalent to 20 unit CubeSat. So there's a lot of advantages. I'm going to skip most of that. If anybody is interested in technical details on it, you can approach me later. NASA is funding a test of those disks, I think either this year or next year. And so we will be able to demonstrate that it can function in near-Earth space. And so we're saying that could be one of those concepts that we can fly out. It's going to be packed into the launch vehicle like this and deployed as a series of disks that could be lined up along the trajectory of Apophis and take the pictures that we would like to collect. The DISSAT is, so this is some of the advantages of the DISSAT here. I'm going to skip this because this is just a basic description of the system, but it's just one of the concepts. We consider several form factors like 6U, 12U, and things like that, or any small sat that we might build to do the job similar to that. And so if we build a series of them, let's say we have 20, so what we're going to do, we're going to launch them and park them in orbits prior to the close approach. And at the right time, we are going to be given a delta V, which will shape their orbit to come close to the orbit of Apophis. So here is Apophis coming close to the Earth. It's being bent right at this point. And we're going to align them along this trajectory in such a way that they're going to be taking mostly optical pictures of Apophis at several spots before, during, and after their approach. The orbits are near Earth-Moon rotating frames. They look kind of crazy orbits, but they do the job. Currently we are working on optimizing those trajectories to show that we can drive down delta V even more than what was computed here is just an example. And so let's just see what's going on our planet today in terms of asteroids that are zipping by. So I did this morning. I put these in a box here. These are asteroids that are zipping by our planet today and tomorrow, just for Asteroid Day. One of them is quite large. It's between 110 and 250 meters, and it zips by a planet closer than the distance to the moon. It is not as close as Apophis and not as large as Apophis, but it is of interest, because objects like these are some of the tens of thousands, if not hundreds of thousands, of near-Earth objects that are out there that were not discovered yet. And so here is an object that was discovered this year, and it could destroy a city or a small country instantaneously if it were to impact with us. And that's happening today at less than the distance to the moon. That's something that everybody should be aware of this possibility, and prepare to mitigate it, to eliminate this threat. But looking at the next 5 years, we see that there are a couple of opportunities to maybe do some testing, demonstrations around some objects. So here's an asteroid that's going to zip by a planet in 2028. It is a sizable object. It's going to come at about 2/3 the distance to the moon. There is another one that's going to zip by a planet after Apophis in November of 29, also closer than the moon. It's not a terribly large object, but all of these objects could be training objects for developing our space situational awareness capabilities. And so another technology that we hope to be able to develop for this mission is something that's called IPNT, which is inverted position, navigation, and velocity. Typically, when you use your GPS, you use the knowledge of the location of the satellite to figure out where you are on the map here on the surface of the Earth. But we want to do the inverse of it and use assets on the ground that will precisely know their location and figure out the location of those spacecraft in space so that we can line them up near Apophis and in any other place in the cislunar space. So that's called inverted PNT. It means knowing the position of the ground assets to figure out the position of space assets. And that's it for this quick introduction. At the end of today, after hearing several interesting talks, time permitting, I can ask some questions and give more information on other things that we do. But with now, I think we should move on to the very first talk, and let's see who that would be.
Is this a good time for questions?
Okay, that's going to be Mike Nolan. And so do we have him online and switch over to?
That's the afternoon session.
Oh, afternoon?
Yeah, Morgan and Luisa has to go.
Oh, they're doing it now. Okay, so it's not in the right order. I see.
Look at the agenda.
Oh, the agenda is here. Right. Okay. Thank you.
Can you log in online?
Oh, Morgan is the next one, right?
Okay.
I think it's Morgan, right? Which is
Morgan.
okay. So yeah. Got it. This is just the BIOS. Okay.
Yeah.
All right. So next one is Morgan. Oh, thank you. All right. Morgan and then Luisa and then lunch break. Got it. Okay. So let's go to Morgan, and Morgan is here. And Morgan. Okay. Let me just quickly read about Morgan. Morgan Goodwin is the executive director of the Planetary Sunshade Foundation. He also serves as director for the Sierra Club's local Los Angeles chapter. Morgan's background in climate advocacy has included international climate conferences global advocacy and local political service as a mayor of Shwaki. Wow. Okay, over to you.
Wonderful, thank you very much. Well, we get the slide pulled up here. Hello, everyone. Good morning.
Hello.
Thank you for having me. I'm honored, and I'll admit a little bit intimidated to sit with a bunch of space engineers because I'm not a space engineer. As you heard from my bio, my background is in liberal arts. I've been specifically working on climate change as an advocate since college. I had a big wake-up moment in 2005. Some of you might remember Hurricane Katrina slammed into the city of New Orleans, and we almost lost an American city due to the overly warmed ocean. But what made even a deeper impact on me was just how disproportionate the impacts of that event and the suffering of that event fell on those who have the least resources, have the least capability to respond. And the realization that for the rest of my life, we would see an increase in climate change destruction and suffering, and that the poorest people in the world would suffer the most from that. So I have been seeking ways to advocate for climate solutions for the past really almost 20 years now, which makes me feel old. That's often involved advocating for policies to increase renewable energy production, increase public transportation, decrease and block the extraction of fossil fuels. And that work is important. And I'll get into a bit of how that fits in. But about a year and a half ago now, the last couple of years, I was asked to take on the leadership of the Planetary Sunshade Foundation because of my background in climate and environment, and because of my skills in organizing people to achieve political ends, which is what this project is. So this is going to be a brief overview of the concept, the planetary sunshade. Quick show of hands. Before the talk today, how many of you had heard about the planetary sunshade as a concept? A couple of you. I met you a few last month at a conference. This is the only slide I have on this topic. Climate change is bad and it's getting worse. I'm not going to go to details, but I would simply say that the planetary defense nature of this gathering is why we are here. While the planet is going to be fine, our civilization is not equipped to withstand the impacts of a world that is 2 degrees Celsius warmer, let alone 3 degrees or 4 degrees, which is where we're headed at current rates. And I quite like our civilization. I think it should continue. I hope you all agree with me on that. I think you do, based on the work you're doing. And so, how do we defend our planet? How do we defend against this threat? One of the things, and I'll get to this more, is we need to reduce our carbon emissions. And so, the preface, the disclaimer for this whole talk is that nothing I'm saying should in every way be construed as a substitute for for discontinuing use of fossil fuels and getting our carbon dioxide levels in the atmosphere down to safe levels. This is the sunshade is a ventilator to keep the patient alive, while the actual medicine that we need to do to heal climate and its related impacts has time to work. The red line here, if today is our where our global temperatures are right now, corresponding to the level of greenhouse gas emissions in our atmosphere, the red climate trajectory is the track that we are on now. This is the track toward intolerable climate impacts. This is what it looks like if we continue to burn oil at the pace we're burning it, burn coal at the pace we're burning it. If OPEC gets to continue as usual, and if Wyoming gets to keep mining coal, and China gets to keep building coal plants. The orange line is what most environmentalists are focused on, and rightly so. This is the path to zero emissions. And this is important, it's critical. This is if we succeed in switching everything to clean cleanly produced electricity. As you'll see, that orange line is still quite high. And so we also need to clean up those past emissions. We need to extract carbon out of the atmosphere, often called carbon capture sequestration. We can do that through natural means, planting forests. We can also do that by industrial means. But this gap here still gets us above that intolerable impacts line. And this is a thing that most environmentalists don't like to talk about. And so the solar radiation management describes the suite of ideas of how we reduce the amount of solar radiation impacting the Earth, which corresponds to temperature. And you'll see this equation down below. This is the temperature equation. Temperature tomorrow is starting where we are, plus the amount of released emissions, the amount of released reservoirs, the future emissions, minus the emissions that we remove from the atmosphere, minus the amount of radiation that we can actually manage. The sunshade is a space-based option for solar radiation management. A 1.5 to 2 million square kilometer sunshade stationed at Lagrange point, Earth Sun Lagrange point 1, corresponds to roughly 1 degree Celsius of global warming. It's a very simple concept, right? If it's a sunny day and you want to cool off, you might put up an umbrella or a sunshade. This is that concept for the Earth, and it's simply working backwards to say, well, how big does it need to be to achieve a certain level of cooling? It's not a single element, although we talk about a sunshade. It would be quite absurd to try and build a structure that large, but rather, how do you build hundreds or thousands of 10 kilometer or 50 kilometer kinds of shades to achieve that effect? The location, I don't have to explain this to you all, but I often speak to non-aerospace people. They say, why can't we just orbit this around the Earth? And that's obviously because if you orbit it around the Earth, it would only block the sun for 1% of the time that it was in orbit, whereas if it's at Lagrange 1, it's 100% of the time, 24/7. The other interesting thing about this point is that it's far enough away, but the shading is not acute. Rather, the umbra does not reach the Earth, but the penumbra covers the entire Earth. And so the shading is not only, we don't have any spots, so you don't have like a total solar eclipse spot, shading different countries at different times, but you also have a general shading, which means that you would reduce a lot of the geopolitical issues that come from some countries feeling like they are being treated differently than others. This also has the climate benefit of having the minimal disruption on weather patterns, right? Because the last thing we want to do is heat one part of the Earth and not the other. That creates winds and ocean current disruptions that can have impacts on monsoon cycles, that can have impacts on agriculture. Again, these are things we're trying to avoid. Talked about how this is modular. This is many thousands of spacecraft. We've talked about the size of this project is intimidating, to say the least. We could do this launching exclusively from Earth, although the carbon impacts of those spacecraft launches alone start to become significant and counterproductive to what we're doing. We think that using and exploring the use of space resources, both from the moon and or near Earth objects, is a place where most of the raw materials could come from. So you could imagine a construction plan where the avionics and control devices are manufactured on Earth, but the vast majority of the bulk, which is likely a sort of aluminum-like substance, it doesn't have to be very high quality. It simply has to be achieve the function of blocking sunlight, comes from space resources, and the process by constructing that would be an industrial base, which could be used to construct any other kind of space object. The spacecraft, because sunshade spacecraft are by definition intended to catch as much sunlight as possible, whether we like it or not, they are solar sails. Solar sails, as we know, is an exciting technology that allows us to send spacecraft all over the solar system without the need for heavy and expensive propellant. In this case, this is an advantage to us because the Lagrange 1 point that we're talking about, or Sun Lagrange 1, is not perfectly stable. If you want to have a spacecraft at Lagrange 1 for any long period of time, you need to have some mechanism of station keeping. And our studies show that we can use the solar wind and the solar sailing mechanisms to control that position. So these spacecraft should not need additions of propellant, should not need refueling, which is important considering the scale. There is an interesting trade-off. I don't have the slide for it here, but with many of your engineers, you'll know this. Because of the solar pressure, these spacecraft actually do not sit at Lagrange 1, they sit sunward of Lagrange 1 by as much as 50% further away from Earth. And that's because the gravitational pressure that creates Lagrange 1 is offset by the solar radiation pressure, so you need to balance that out by being closer to the sun. The heavier the sunshade is per square meter, the closer to Lagrange 1 it is, whereas the lighter the sunshade is per square meter, the closer sunward it is. But it also changes the size that you need. Because if you're sunward, you actually need to have a larger sunshade in order to achieve the same effect. And so there are some advantages to having this be a heavier structure. And we have, optimal distances that we can map out for that. But it does come back to the benefit of using space resources, which we would imagine would result in a lower quality and therefore heavier per square meter object, which is not necessarily a bad thing in this case. But these are interesting questions that will result in many PhDs written in coming years. So we've talked about climate change mitigation. In terms of planetary defense kind of concepts, the other main kind of interesting benefit, in addition to early warning of solar storms, early warning of coronal mass ejection measurements, right now the soonest that we can actually get measurements on coronal mass ejections is about 20 to 30 minutes, just based on the distance of how fast they travel. Because the sunshade is sunward of Lagrange 1 by as much as 50%, that gives us a 50% longer timeline in advance of that sort of measurement. However, to think, many, many steps removed, a sunshade could actually be used. And there's ideas of how you could create a artificial magnetosphere, which could block those, actually protect the Earth from those kind of coronal mass ejections. The sunshade, in terms of space solar power, again, we have large flat surfaces facing the sun. If those surfaces were designed and manufactured as photovoltaic cells, the sunshade becomes the largest electrical producing object in our civilization, which means that any kind of industrial process that requires a great deal of electricity could be co-located at a sunshade at Lagrange 1. Again, ideas for this are very large data centers, more space resources production. How do you turn bauxite into aluminum? You need a great deal of electricity. If you have unlimited electricity, then there's benefits to that sort of co-location. And all of that speaks to the development of a cislunar industry. We have lots of ideas of what a cislunar industry might look like. What we do not have is a sufficient investment to get that industry off the ground. And maybe saving our civilization from the threat of climate change might be a sufficient rationale for our governments to invest in that level of industry. This has been talked about for quite some time. James Early was the researcher who first presented this concept to Congress in 1989. It's been studied repeatedly over the years, and there's been academic literature at a fairly steady pace. However, the drastic increase in the climate impacts that are being felt and our awareness of climate change, combined with the rapidly falling cost of launch, means that the feasibility of a sunshade is much more feasible than it was, and the urgency to do so is also much greater.
So what were the units of cost on the far right? $1 trillion. Okay.
Yeah.
Okay.
Yeah.
Was that 1989 already about global warming?
It was, yeah. Yeah.
Early.
Yeah, the climate scientist Michael Mann had presented on global warming to Congress a year before that, and it was pre-political, right? It was simply, oh, here's an interesting problem. How do we fix it? And we started to kind of think about ways to fix it. Yeah. So the Planetary Sunshade Foundation that I run, that I was asked to take on, is primarily made up of aerospace engineers around the world. However, our agenda is to bring the sunshade into reality. And so we are here to advocate for people to join us in this mission. We think that the aerospace industry and community has an interest in our civilization continuing, therefore an interest in our climate being stabilized. And we think that space has a role to play, and a really exciting role to play in the climate fight. More concretely, we believe that our government can and should invest in developing this concept. There's a very specific mission that I'll get into in the next slide called the Solar Cruiser mission that NASA should fly as a prototype of the sunshade. We believe that any and all efforts to develop a robust in-space logistics and in-space cislunar economy is helpful. It makes the sunshade more possible. It brings those cost numbers down, and that NASA should continue scenario planning and getting us ready for that. I mentioned the Solar Cruiser. This is a heliophysics mission that takes advantage of the phenomenon I described of being 50% closer to the sun than our current spacecraft at Lagrange 1. And it is a technology demonstration mission. So it's designed to demonstrate the capability of unfurling a very large sail in space. This would be an order of magnitude larger than the largest solar sail ever flown. It'll be the first solar sail flown outside of low Earth orbit specifically, but even more importantly, it's actually designed to fly at Lagrange, Earth Sun Lagrange 1, and demonstrate the ability of the solar sail to control its position in that location, and actually modify its orbit. And this is less relevant for the sunshade, but just fascinating from a orbital mechanics point of view. They believe that it can modify its orbit to the point where it can actually get better observations of the sun's polar regions than you could achieve with a propellant rocket. So it would teach us incredibly valuable information about what it would take to operate a sunshade, right? The fact that this mission is half built is one of the most fortuitous coincidences for the planetary sunshade effort that I can imagine, because getting to the point where we have NASA developing a prototype mission, would take us years and years, and yet they already have this. Unfortunately, the mission was determined to not meet a technological readiness review a couple of years ago, and so funding was pulled. As you can see, a lot of the spacecraft is built, and we think that with the added reason of a climate effort as significant as the sunshade, that we can get Congress to chip in the funding needed. We have support letters from Department of Defense for why they want to see this mission go forward. from a space weather detection standpoint. And we have a launch window in 2028 that we are still aiming for. And we work closely with Les Johnson, who's the project investigator for NASA on this mission and helped develop it. And so this is an exciting time for us. Our organization is going to be in Washington, D.C. Just in a few weeks. We have meetings scheduled with the White House Office of Science and Technology Policy. We're meeting with the State Department's Space Affairs Division. We're meeting with several members of Congress and congressional committees to make the case and give them presentations very similar to what you're getting now, probably with a little less of the engineering. We are building our organization through fundraising. Love to meet philanthropists that are excited about a game-changing idea. We are testing messages so that we can better communicate to the public to build that public support. We are currently, we're exploring university partners that want to invest in grant funding for PhD and postdoc research to advance the concept. I had a great talk with the head of space at Virginia Tech just this week, and he's exploring what it would look like to bring this sort of sunshade as a focus for their space program. And the core of our organization will continue to be organizing supporters. So again, we're a voluntary network of mostly aerospace engineers who are studying the concept and discussing how we can advance this. And if that sounds like something that you might be interested in, I would be thrilled to have you join us. So thank you for your attention. How much time do we have, by the way?
I think we are at time pretty much, but we can take a question or two.
Okay. Yeah.
Yeah, I was curious about the mission that was didn't have a high enough TRL. And was that a NASA Marshall flashlight for a lunar flashlight or something? There had been some solar sail that started being developed, but what was developed halfway?
The mission is called Solar Cruiser.
And it was called that before?
Yep.
When it was, okay.
Yeah. Okay. Yeah, the Solar Cruiser mission is, I can send you a bunch of, I can send you NASA's latest presentation on it if you like. Yeah.
And is that NASA Marshall? Or where is it?
Johnson.
Johnson, okay.
So.
Taking questions?
Yes.
We have a question online from Joe. Would you like to speak up?
Yes. Can you hear me okay?
No, just a moment. We are trying to set up
Little
volume here.
Can you hear me now?
Yeah, now we can hear you. Go ahead, Joe.
Okay. I'm looking at this and asking myself from a geopolitical standpoint. This is a very large target, and it would be vulnerable to attack. And if it also is providing power to the population on Earth, it could have tremendous geopolitical effects. Have you considered those?
Yes. I'm guessing that you might be asking me to elaborate a little bit on that consideration.
Yes, please.
Yes, thank you for naming an important factor here. Climate change is a global solution and a global problem, and the solutions need to be global, and that means they need to be geopolitically, coordinated, whatever that looks like. I believe that the International Space Station gives us a good step forward in terms of thinking about what does international collaboration look like on large space projects. The Artemis Accords obviously take a step further, although let's acknowledge that the Artemis Accords do not include the major spacefaring country of China. So in a best case scenario, this project is really co-led and co-produced by the two major space powers, the US and China, along with supporting elements. That's a best case scenario. To kind of back out a few, not less than best case scenarios. It's not a single object vulnerable to attack. Even a catastrophic event might remove one or a couple or tens of these solar sail spacecraft, which are in and of themselves, 20 square kilometers, let's say. And so it's not like there's a single point of failure. But I think the larger question here that you're pointing to is that this is not just an engineering problem. This is a political problem. This is a legal problem. This is a challenge for our very civilization, I would say. So lots to explore there, and thank you for the question.
Another question?
Another question. There is a question here on site. So let's take a question on site from Rico.
Thank you, Morgan. Great presentation. So I have two questions. My first question is from a technical specification. And I know you were quite transparent on the engineering side, so I appreciate that. But my first question is very technical. Is there any studies, or does your team and your community have an idea of what the life cycle of a solar shade is? Are we talking about a 3-5 year life cycle? And the reason why I mentioned that, when we've gone and done studies or investigative work or technical work like the Boeings of the world in terms of solar panels, I think we're only at like a 47% on the solar grids, right? On the on how much we can utilize the panels. But then there's also an inherent life cycle, right? So do we have an idea on the technical side? What is the life cycle of the solar cruiser and the panel itself? Is that like a 4 or 5 year life cycle?
The quick answer is more research is necessary because the technical specification for this is blocking sunlight.
Okay.
We're not asking it to do any terribly complex stuff.
Okay.
So we think this is an individual sail element might have, say, a 50-year life cycle, and it'd be sort of a constant process. Another analogy would be to think of like a large dam on a river.
Oh,
right?
Okay. Okay.
Maintenance is necessary.
Yes.
You can't just ignore it.
Thank you. Thank you.
But-
Maintainability.
But once you construct it, it's a fairly straightforward thing to manage.
Okay, super. And my other question is personal question. This is aside from my work in the Space Force, and these are lessons learned that I learned and best practices in my career so far. Have you guys looked at the possibility of leveraging this onto a space economy model? And I have to tell you why. It's because I had a chance to work a really amazing program where we were looking at building a space commodities exchange and creating a market, a stock market for space, if you will. One of the most amazing programs that I worked. And I had a chance to learn a lot of lessons by failing. And one of the things that we learned, that there's a lot of amazing, great technologies that folks like yourself and your organizations are doing. But in the American system and our capitalism system, if we do not monetize some of these projects, you can't thrive on investor funding. You cannot thrive on just government funding. There needs to be like a market force. And so my question or proposition would be, is there a way we can economize this to garner or pull power and then direct the power from the sun to be transported to Earth as a power resource? Does that make sense? Over.
That absolutely makes sense. The question was about, is there a way to monetize the sunshade itself? Yes. And the more of an in-space economy we have, the easier it is to build. The sunshade itself has economic benefits. However, your question also speaks to the question of climate change, of how do we monetize and incentivize people to solve climate change? And there are a lot of ways to do that, but the core of it, I believe, will still be government funding, much in the same way that we fight wars or other things that affect us. And once that mobilization happens, it will have many, many positive economic benefits. But our core value proposition here is that this is a public government investment in our own survival. And we can all help make that cheaper and have more benefits. So I want to make space for other speakers. I know we have lots of questions, so I'm excited to chat over lunch. Thank you.
Thank you very much. Those talks are intended to be starting points for additional discussions. So anybody interested to get more information, please approach Morgan. He shared his contact in one of those slides. So just touch base with him for additional information and questions. Thank you so much. All right, we are going to Thank you. We are going to move forward to the next talk, which is by Luisa Fernanda, which is waiting online. Her bio is quite large here, and so maybe, Luisa, would you like to speak about yourself a little bit instead of me reading your bio? And thank you very much for joining us. If you are online, I think we are setting up.
Okay, can you guys hear me?
Yes, we can hear you very well. Welcome to our conference.
Thank you for organizing it. It's been very interesting to hear. I'm going to talk about a different threat, not a climate threat, but kind of another threat that we might face, which are asteroids. So yeah, my name is Luisa Fernanda Zambrano. I'm a planetary scientist at the Florida Space Institute. I used to work at the Arecibo Radio Telescope, which I will talk a bit about today. I am an ISU, International Space University alumni, and I've done research on different areas of astronomy, and now just focused mostly on near-Earth asteroids, especially those that rotate really fast or that we have radar data for. I'm also very interested in education programs, high school teaching, high school programs, and of course, the rendezvous with Apophis, which is coming up really close. So anything Apophis, I'm super excited about. So yeah, please feel free to ask me questions if you want as we go. I can't see the Q&A here with the numbers, but if the moderators would like it to be at the end, that's fine as well, okay? Can you all see my screen good?
Yeah, you sound good and you're being heard very loudly, so please proceed.
Okay, well, I think we all know about these rocks in space. I really like this diagram from JPL. It's a few years old, but it shows the amount of rocks that are there. Space is really big, but there are a lot of rocks in space. So, and asteroid research is one of the things we do at the University of Central Florida, the Florida Space Institute. We're very interdisciplinary at FSI, so we're also very open to collaborations and new ideas of projects, of mission concepts, of CubeSats, or things you would like to develop. I specifically work in the area of planetary sciences, like I said, studying near-Earth asteroids. So I'm going to talk briefly about general information about asteroids, how we saw them from Arecibo, and what radar can tell us about these objects. But first, I usually like to start with this little reminder of where we are. We're in a planet, but our planet is in the arm of one galaxy. Like it should be somewhere around here where our sun is, where the arrow is pointing. And this is just one of billions and billions, trillions of galaxies that we know of. This is a deep field image from Space Hubble. I know we're gonna get so many, we've recently gotten so many beautiful images from the James Webb Telescope, but I really, really like this one from the Hubble. It really gives you a perception of like where we are, like, how tiny we are and how big space is. It's really, really big. One of the celestial objects that humanity and civilization has been fascinated by throughout time have been comets, as a type of rock in space that this rock is made of certain materials that are in an ice state until it comes close to the sun or some heat source, and then these ices don't even go through the process of liquidation, but they go straight from being a solid to being a gas. So when we see comets, there are these rocks that are hydrated in ice mode. When they come close to the sun and that ice starts melting really fast, it goes in sublimation, we see these tails, these beautiful tails. And that has always captivated civilizations. They've been the omens of disaster and destruction in the past. But as we've learned more about them, we actually had the opportunity, before I go there, as we've learned more about these objects, we know that they're formed in something called the Oort cloud. I mean, we're very familiar with our solar system in this atomic model, in this planar form, where we have the planets, we have, a main belt, and we have an outer belt called the Kuiper belt. And we theorize this an even bigger, not belt, but a whole bubble cloud called the Oort cloud, where most of these comets come from. We had the opportunity to visit a comet years ago by the Rosetta mission. This is comet 67P. And here you can really see that outgassing process that I was mentioning. To me, these images are just spectacular. When we received those images, when that mission was happening, I was just mesmerized by how beautiful it looked. But let's talk about the rocks that are closer to us, okay? So the rocks that are on the near Earth object population. These will be the objects that are located in the main belt, what is called the main belt, which is the region of rocks that is between Mars and Jupiter. And those rocks, we care about them because they come in different shapes and sizes. They're not all the same size. Some of them come in pairs, some of them come triple. This is a potpourri of images here of some of these rocks and some of these asteroids. For example, Ceres, we were able to visit with the mission Dawn. It did a quick flyby, and we can really see regions that are very bright, and we see a lot of impacts that this guy was in combat for some time. We see that they could be round, or they could be, like I said, come in pairs, or they could look more like peanuts. Like this is number 7, Itokawa, which is the target of the mission that was visited by the mission Hayabusa. So in general, these asteroids are small rocky objects that orbit the sun, and they're, of course, much smaller than planets. Here in the middle, we can see an image captured by the OSIRIS-REx mission as he was approaching Bennu. I think he was, while they were studying it, of the asteroid Bennu. It's just incredible to see these images of these rocks in space. And on the top right, you can see a close-up image of the asteroid Ida taken by the Galileo spacecraft several decades ago. But some of the objects that we care about mostly are what we call PHAs, potentially hazardous asteroids. But it's not because they're asteroids that are actually going to hit the Earth. Those we call virtual impactors. And we have programs that are actively monitoring the new discoveries to know if they could be of potential impact to Earth. But these PHAs are asteroids that could pose a threat. It could be asteroids that are greater than 140 meters and that they can get closer than 19.5 lunar distances. Remember, space is really big, like really big. So 19.5 lunar distances is a really, really huge space. That's why we're also very interested in Apophis coming, because it's coming really close to Earth. I mean, it's close, but it's still really far away. It's like between geosynchronous orbit and Earth, which is closer than the moon. So it's really interesting to see an object that close. And we care about this because there's many we have discovered. Right now we know of about 35,000 near-Earth objects, and about 2,500 of them are PHA. This image, I made it using artificial intelligence chat thing called Hotspot AI. And I asked it, I prompted it to give me, humans and dinosaurs running away from meteors or constellation of satellites. It took some work for the AI to really grasp it. It mostly gave me T-Rex dinosaurs, which I specifically asked it not to, but it's really interesting. I find it really funny to see this image because, there's no dinosaurs now, but we want to be ready in case there's an object that could come and impact the Earth, because we know they do. Actually, on average, meteors enter the atmosphere at rates of like every 30 seconds. You can have something that's a millimeter big. And these are called micrometeorites. They bombard the upper layers of the atmosphere, and they they just deposit their components because they disintegrate. And that's also a topic of study that we used to do at Arecibo. But we really care about the ones that are bigger, the ones that are more than a meter, more than 100 meters, more than 10 kilometers, because if they were to fall in a populated area or close to a shoreline, but there could be a populated area, it could be very not good for society, for civilization. But we've gotten really good at detecting these objects. Actually, since 2008, we've detected 8 objects before they actually impacted the Earth. They came in through the atmosphere. This is 2023 CX1. It's a beautiful picture taken on the southern part of the Netherlands. And it was a few hours before it entered that we knew it was coming and it was going to hit. It was on the smaller size. But we do have sensors monitoring the Earth continuously. This is, for example, the fireballs reported by U.S. governments. The red one is the Chelyabinsk event in 2013 that we all remember. You see, there's really not a preference where they're going to fall. They just fall where they're going to fall. Luckily, the planet has a lot more water than land, and cities are constrained to smaller groups. So that's pretty good for now, right? So something we really want to know about all these rocks is what they're made of. And that's something that Arecibo was really, really good at. We didn't discover this telescope, these asteroids. Asteroids are discovered by optical surveys. They don't emit their own light, so you need the light of the sun to illuminate them and be with your telescope at the right time to be able to see the object. So once the objects were discovered by optical surveys or infrared surveys, then we will get the information at Arecibo. And for those of you that don't know, Arecibo Observatory is located in Puerto Rico. Arecibo is a municipality of Puerto Rico. It's that little island in the Caribbean. The telescope started operation in 1963, and it was a facility that initially was used to study the upper layers of the atmosphere, to understand how radio signal communication worked. Back in the 50s and 60s, that was big development on that, especially when we're talking about the war times and communicating or intercepting communications from allies or from foes. So with time, Arecibo's capabilities got enhanced to go beyond just doing ionospheric studies, and they moved on to doing astronomy studies. So we were just like listening, like a big ear, listening for any radio waves and any radio signals that would come from the sky. Later on, we added a transmitter where we were able to use the instrument not just as a passive instrument receiving the signals, but also transmitting our signal and being able to control that signal that was sent. The telescope was 305 meters in a single dish with a platform that hung 150 meters from the reflector. There were 38,000 individual panels on the surface, and this is what it looked under. It was really, really beautiful. After it was created, there were endemic plants like orchids and dwarf ferns. They terraformed land within decades. This area, which is what I was showing you in what I showed you on this picture, this platform here, that was really like a 3-story building. And inside of that is where it housed most of the instruments, like this red tube that you see on the left, that's called a klystron. It's pretty much an electron gun, like a particle accelerator, a linear particle accelerator that would shoot beam of electromagnetic wave that we could modulate and we can encode if we need it, with a power up to 1 megawatt. It was very efficient. So really we had a 500 megawatt output for each one, and we had 2, so we can transmit up to 1 megawatt power. This is a picture when we got this new klystron and we were lifting it up and taking it inside the dome where the receiver, the transmitter, and different instruments were at. So like I said, pretty much, you get your transmitter and you send the signal, hit it to the object, and we had the capability to determine, we knew very well characteristics of this wave we were transmitting. It was circularly polarized. We knew if we wanted to modulate it or not, if we wanted to embed a code or not. And when we received the echo from both polarizations of these signals and we compared it to what we transmitted, we could get information about the surface of the object. So we transmitted it, hit the object, and then we get that echo back. And with the echo, you have information, precise information on the velocity of the object with respect to you, to where we're observing, and with respect to its distance. So very precise information in the orders of like meters per second for an object that's traveling kilometers per second to meters in distance for an object that's thousands of kilometers away. So when we transmit our signal without modulating it, so just continuous wave, I like to give, when I do this to the general public, I don't know everybody's background here, but I like to make the reference of a radio station because we are more familiar with that. So when we have a radio station, we tune our car to the right station, we can hear a song. That's because the song comes in that wave, and then our car has a machine that decodes it and makes it into our song. So we could choose to not put a song in our signal. We just transmitted the signal directly. It hits the object, and when we get the echo back, since we know where we have a prediction of where the object should be, so any difference from that prediction to what it is gives us an insight of maybe a change or a differential in the velocity the object was going to. So we quickly submit those possible changes and then try again. And once we get it that is centered, we know that the object is at the exact velocity the object is traveling. So this is really, really important because it prevents objects from being lost. And sometimes, when optical telescopes discovers these objects, they have, the margin of error in their location is pretty significant. So let's say we want to, sorry here. So let's say instead of just transmitting the continuous signal, we wanted to embed a song in it, a code in it. That will give us then information, more information about the object. We could have a time delay, like we can know how long it took the signal to get to a specific point on the object. And we could also have that information about the velocity. With those two parameters, we can then create kind of like a map of what the object would look like, knowing that, it's a little bit tricky because 2 points can correspond, the same point can correspond to two different locations in the different hemispheres of the object. But still, you've seen really cool computer software and statistics were able to use those signals to create images like this, for example. This is near-Earth asteroid 2014 JO25, which is a contact binary asteroid. It's a PHA. We know that is about 870 meters long, and it's a really good measurement of its size based on the delay depth that we get from our measurements in radar. We can calculate the rotation period very accurately. And we know this guy did its closest approach in 2017, just 4.6 lunar distances away. And we can have great detail about like the characteristics. This is akin to having a flyby of a mission for some of these objects. Then we have other objects like, for example, Phaeton. Phaeton's pretty famous because is believed to be the parent body of the Gemini meteor shower. So like maybe theorized that maybe Phaeton was an active asteroid, or at some point started losing some of its material and then just left it. And that's what we see of the Gemini meteor showers. But it's the target of the Destiny Plus mission, a mission to an asteroid from the Japanese Space Agency. This is the second largest PHA we know. And it was actually the first radar observation we were able to do after Hurricane Maria hit Puerto Rico. The diameter is about 6 kilometers, so it still goes into, it's pretty big object. Another cool thing about radar is that we could see some features, like I mentioned before, we could see some shape parts. Here we can see some, you know, some things going on here, right? There be a ridge near the equator here, this dark spot, could it be a crater or could it be a mountain? We can have some more detail about it. Like I mentioned, and being akin to a space mission, on the left is the radar model of Tutuatis, and on the right is the actual spacecraft image from Tutuatis, from Changi spacecraft. So it's for a fraction of the cost, it's pretty good. Like I mentioned earlier, you know, radars, sometimes these objects come in pairs or in triples or quadruples. Radar is a really good technique for finding these satellites. These are two examples, QE2 and Atira. Or sometimes they come in three, like this one here. We found Florence. It was a beautiful observation that I got to be part of. This was the third triple NEA known when we discovered it in 2017. It is 4.5 kilometers and at the primary, and the moons are significantly smaller. So kind of what we learned with Arecibo, I'm going to add this here in case you're interested. The NASA ADS has some nifty, really cool features where you can see how papers are correlated by topic or by author. So I took advantage of that and looked at it for Arecibo. So of a network, here's plotted only the first 1,000 papers of Arecibo and the word radar. Remember that Arecibo is a facility that was used for 3 areas of science: atmospheric sciences, astronomy, and radar. So there is an interconnection between the 3 areas and in the publications. And when we do, like I mentioned, you could also do this connection of networks of authors. And that's also pretty interesting because you get to see, like, you know, the pioneers on the fields and their discoveries, and like the new people that are coming in and how their work relates. So with Arecibo in general, in total, while it was going, while it worked as a planetary radar facility, we were able to detect about 1,028 objects. That includes the moon, Mercury, of course, Venus, Mars, some of its moons, Saturn's rings, the Galilean satellites, many main belts, about 800 near-Earth asteroids, comets, and even spacecrafts. So with Arecibo, we were able to obtain a lot of information that helped write a lot of theses that helped us understand more how asteroids and comets are leftover rocks from the formation of the solar system, that we can continue to study the early solar system, how its evolution, how these orbits have changed, how these objects sometimes get accelerated or not. We had produced some of the best observations of asteroids and comets, and deriving all this physical information, it's really, really good. So with that, I thank you. This little flash that I think you see it there, I hope you got to see it. That was a near-Earth asteroid, a meteorite coming into the north coast of Arecibo a couple of years ago, in the south of Arecibo a couple of years ago. And this is what the control room looked like and how observations actually happened. So with that, if you have any questions, I'll take them.
Yes, I have a question. Can you hear me?
Yes.
Oh, good, beautiful. So I've been in Arecibo a couple of times, but as far as I understand, Arecibo is not working right now.
Correct. Yes, and the facility collapsed. One of the cables collapsed. The main cables collapsed in December 2020, and since then the facility has not been operational.
Is any plans to repair all the equipment and put to work again, or Arecibo is dead?
Well, as for the instruments, some instruments we've been able to salvage them and move them to other facilities. Other instruments were, for example, now are in Culebra, where we have a small facility. The rest of the like the dish and transformers and all of that, it will be a question that I would love if you sent it to the National Science Foundation, see if they actually give us an answer. But I know that the visitor center was awarded, what used to be the visitor center is going to be an education center called C3, focused mostly on computer sciences and biology, and is going to be directed by an amazing Puerto Rican astronomer, Wanda Merced. But we really don't have any updates or information about, but much more than that on what's going to happen there.
Okay, thank you.
Thank you. Any other questions from, Mark, go ahead.
I have one question, and it was, I was here last year and presented some ideas that one could do basically the same thing with a laser telescope that you do from Arecibo. If you were to modulate the laser, just like you modulate the radar, and that you can have a much finer image with laser light rather than radio waves, which are much larger. So you might be able to illuminate something precisely and get a very tight response, and even see locations that you like next to the sun where you can't, you get a lot of radio noise there, I think. So what do you think of that? Does that seem reasonable?
I haven't seen your specific presentation or work, but I think sounds really, really exciting. We will need a location where you could do such a transmission, maybe a bit of further study on the constellations of satellites that are on Leo and how, if there'll be any interference, also how fast we could track with that instrument. But sounds like a very interesting topic.
Yeah, it seems like equations work for radio and electromagnetic light waves is basically the same, just on a small scale.
Love to learn more about it.
Yeah, okay.
Thank you. Any other questions for Luisa? Yes, out there. Maybe you can come out here and talk to the mic so that everybody can hear.
Yeah.
Hi, Luisa. Thank you for your presentation. Very interesting. I had a few questions, but I'll ask the first one here. Could you speak on the usefulness of space-based optical imagery for NEO asteroids from low Earth orbit? Is this practical or useful, or is the imagery only useful mainly reserved for multi-million-dollar or billion-dollar specialized spacecraft? Or maybe is just the SSA data useful compared to radar data that you're collecting from Arecibo?
I'm not sure I understand, like how useful are space-based optical images, like using the LSST for studying NEOs, or?
Yeah, like optical imagery from low Earth orbit.
From low Earth orbit. That sounds, it sounds very useful. Can you track? How would you do the tracking?
Yeah, using, let's say, for example, the a priori knowledge from your radar dishes for the initial position, tracking those objects with LEO spacecraft. Is the images from LEO, given like the practical pointing errors and knowledge positional errors from LEO spacecraft, would those images be useful? Or, I mean, the fidelity of your radar instruments, like down to the meter per second, is very very fine, and the optical imagery might not be as high fidelity, but with the addition of the data fusion from the space-based imagery, be useful in any type of scientific studies.
Well, I think, Mike wrote what I was thinking, like what type of telescope, what would be your optical system? Would it be, will need to be pretty big to resolve these objects, unless you're talking about only objects that are like very, very close to Earth, or like further out, because you will need large telescopes.
Yeah, and the more like smaller telescopes, like for small sats or nanosats, like would those space-based imagery be any type of use for scientific research on these asteroids, or is it mostly reserved for large rendezvous spacecraft that you can get more resolved imagery from.
Maybe this is connected in some way with the passage of Apophis in 2029, where everybody take optical measurements of Apophis during this flyby. You can say a few words about that particular event, Luisa?
I guess it will go down to the resolution your cameras have, like how powerful these cameras will be, you know, how sensitive they will be to the object. I guess if you're putting context of Apophis, are you thinking of having like a constellation of Leo telescopes that when Apophis passes, they're all observing it? Maybe do it by occultation instead of trying to image it directly, kind of see some occultations of it. I don't know. Is that kind of what you were thinking?
Yeah, it's a similar type of question. I'm just trying to like similar for the Apophis flyby. How useful would, let's say, Leo observations using optical imagery from low Earth orbit be for something like a flyby or NEO objects that might hit Earth? Would that augment radar data that's being collected?
I think it will be useful if you have a good resolution. You can guarantee some sort of like good resolution on your images. Remember also that radar was an active technique, so we're transmitting a signal, it's interacting with the object, and then we're getting something back, right? Optical, it's passive, you're just pointing and collecting. And the sensitivity of your sensor is what will give you, you know, that better image, a better resolution or not.
And then I have one more question, if that's you don't mind. So another question I had was, and you spoke a little bit about this, where you tuned your Doppler shift frequency, your center frequency, to match the known a priori knowledge of the asteroid. But what's the strategy for detecting these objects in the first place? Do you guys do like general sweeps with the Arecibo radar dish, or do you like how do you filter out the noise, the background noise from potential unknown objects, and then classify them for future observations?
So when the asteroids are discovered, we don't discover them, right? We have a beam of light that is directed and it's, you know, focused. So we don't have like full open width for the whole sky, or we don't sweep the sky with our beam the whole time to find objects. Optical surveys find them by the reflection of light by looking at the sky all night long, and they know where each star is. So if something passes that is not a satellite or a constellation of satellites, it's probably an asteroid. And then we get that ephemeris information, that say address, like where they said this is located here and is moving this way. So we get that information. And when we do our radar observation, we try to focus our beam in that general direction. Now, our signal is not gonna, the radio signal is not gonna interact with just anything, right? So once we hit the object, it's like in the slide I show, we show like a peak of the signal. We can see it pretty clearly because there's really not many more things around. Remember, space is pretty big. So once we get that address, you know, our beam is bigger than where the object is, so we are able to say specifically where it is.
So if I understood it correctly, the first step is to discover those objects by optical telescopes, followed up by some radar measurements to augment that, and that could be followed by in-space additional measurements to you know, improve the measurements that we have on these objects, sort of like a three-step type of process.
Yeah.
Okay.
Yeah, thank you so much.
Reobserved from ground base or reobserved with radar.
Thank you, Luisa. One last question before lunch here. So, Mark?
Yeah, thanks. And I liked your presentation a lot. And I used to work with Jean-Luc Margot, who had been at Cornell and did radar work out of Arecibo. But this question is something else. You showed a picture of this asteroid Florence, right? And it appeared from the picture, and when I look online, I see it also, that there's a crater at the very tip of the, you know, it's an oblong shape, and there's a crater at the tip. And I've wondered about a similar body, the inner moon of Phobos, of Mars, right? that also has a crater at the prominent point. So it's not where you would expect a crater. It's like this elongated football-shaped kind of an object that then has the crater right at the tip. And I wondered in the past if that might not be an impact crater. It might almost be like a spinning separation scar or something like that, like an umbilical scar, you know, that it twangs back and into shape. And I was just fascinated to see. So I don't know if anybody else has, you know, wondered about that or you noticed it. Or, but when you had it, pretty good pictures. And I pulled it up online. You can show it again, but it was like, wow, it looks like there's a crater there on the top of the hill, essentially. You know.
Yeah, like that is actually the my next research project. My next paper is to use the radar and optical observations for Florence to try to create a shape model, a 3D shape model of it, and maybe understand more, you know, the surface features, and then maybe see a little bit of its orbital dynamics, like the orbital history, and see if there's any you know, back in time you can trace any events, or if we can see of any relations with the families, or more information on the secondary or tertiary body. Could be a piece of it, you know, just learn more about it. Yeah, I'll keep you posted.
Thank you.
Thank you, Luisa, and everybody else here. Obviously, if there are more questions, is it okay to contact you, Luisa, with additional questions?
Yes, absolutely.
Great, thank you so much. It was great seeing you a couple of months ago and again today. Very, very, very fascinating. We would like to hear about your upcoming research in the next event. With that, we are going to break for lunch now, and we'll be back at around 2:50-ish for the next talk by Mike. Yes? 12:50 Pacific time, which is about 40 minutes away, right? Yeah. And Mike Nolan from the University of Arizona is going to be there. Oh, Mike, are you up there? Can you hear us? I don't think it's now, right?
Yes, I'm here.
Hey, Mike. So is it now or after lunch? After lunch, right? So, Mike, you're in about 40 minutes.
Yes, I just checking in.
Excellent. So we can hear you very well. We'll be looking forward to hearing your talk in about 45 minutes.
Well, the guys better have a speedy lunch.
Thank you so much, Luisa. All the best.
Bye.
So how did this come about? Did it exist before you joined it?
Folks in the Colorado School of Mines.
Okay.
Right. Space Research Program.
Yeah.
Last project. Of course. When the pandemic hit, they started doing all their presentations virtually. So they can conferences.
Yes, yes.
Right, so they very quickly they kind of identified. There's a German researcher for Airbus who's been working on this for years.
Okay.
So they're like, oh, we don't have each other.
Okay. And you, when did you join?
It's a year and a half ago.
Okay. It already existed, and you had an interest out of Sierra Club or Amazon?
Yeah, and I'm friends with the founder. You guys are kind of,
So who was that?
his name is Ross Sanders.
And if you can give us a very quick bio of yourself. Can you hear us well, Mike?
Okay, yeah, I hear you fine. Yeah, I'm Mike Nolan. I am the Deputy Principal Investigator for the OSIRIS Apex mission, which is an extended mission for the OSIRIS-REx. I was called the Science Team Chief on OSIRIS-REx. I've been at the University of Arizona since 2015. Before that, I was at the Arecibo Observatory for 20 years, taking images of asteroids using the Arecibo radar, as Luisa has been telling us. And right, and actually when I applied for the job at Arecibo as a postdoc in 1994, I said that I wanted to go and take images of asteroids that could be used in planning space missions. And so here we are. All right. So my talk is 20 years at Bennu, of Bennu from Arecibo to orbit and home again. And now, of course, we're off to the next asteroid. And I'll give you some discussion of how we got to Bennu, what we did there, and then what we're going to be doing next. If I can figure out how PowerPoint wants to work today. There we go. So this is Asteroid Day, and people have heard a lot of this before, but I want to back up a little bit and say, why are we studying asteroids? What is the point? What are our goals? And they have to do with why we send space missions, why we do all these things. The first one is the origin of the solar system. Asteroids are the main source of meteorites from which we determine the composition of the early solar system. And of course, they're also, at some level, leftovers of the material from which the planets formed. So, right, the asteroids, here's a cartoon of the planets, and the asteroids are sort of broken up bits in here in the middle between, at a few AU inside of Jupiter, outside of Mars. The forces, certainly at this point, Jupiter and Saturn put enough stirring into this region of space that planets aren't able to form there. That's probably not why they didn't form there to start with, but that's sort of how they keep getting stirred up now, and part of how we end up getting samples of them. And of course, the reason, one of the things we do, so asteroids fall on the ground as meteorites, and when we get a meteorite, we can study it in exquisite detail. We can cut it into pieces. We can shine any kind of radiation we want on it. We can just do a whole lot of things. But until recently, we rarely knew where these things came from, right? We would have these meteorites would fall on the ground, and we would rarely know their provenance. A couple of cases we were able to compute an orbit, but it was pretty rare. More recently, at least we've been able to see that their immediate orbit right before they impacted, but still we don't really know where in the asteroid belt they came from, with a few exceptions. And this is just to put that home again, right? That you can take you can use microscopes on these asteroids. This image is 5 millimeters across, and you can see all kinds of little things in there. And you can go and do spectroscopy and measure the composition of each one of those little pieces if you want to in the lab. But then of course you still don't really know where it came from, unless you can go figure out how it connects to the asteroids. So that's one, and that's historically that was sort of the main one. And as we all know now, right, planetary defense is a thing. Asteroids present a potential hazard to the Earth, and unlike most hazards, most natural disasters, you can do something about an asteroid, right? There's nothing you can do to prevent earthquakes from happening. You can deal with them when they do happen and make things sort of able to withstand them, but there's nothing you can do to keep them from happening. If an asteroid is if there's a danger of an asteroid hitting, and as long as you know about it a few tens of years in advance, you could just push on the asteroid, and all you have to do is move it 6,000 kilometers, and it's not going to hit the Earth anymore. So if you decide something is a hazard, it is possible and not crazy to just push it out of the way. And so that's why that's one of the reasons it's really worth studying this, is because unlike a lot of things, it's something you could do something about. And the third one is space resources. Again, this was historically seen as probably the flakiest of these, but it is definitely something people are looking at it pretty seriously now. If humans are to live in space, they will need materials, and the most important of those is almost certainly water, which are far more available from asteroids than from other sources. Getting water up into space from the Earth is still thousands of dollars a kilogram, And at that price, you can do a lot. It is definitely worth figuring out how you might get it from somewhere else. And here's a notional picture of somebody going and grabbing an asteroid and taking it off to be processed. All right, so the OSIRIS-REx mission. It's OSIRIS is it's a backronym really, but it's Origins, Spectral Interpretation, Resource Identification, and Safety, and then REx is Regolith Explorer. It's on there because when so originally this mission was proposed in one program, and then we decided we're not successful there, and decided to propose a larger, more complete mission to a program with more funding, and we added REx on there just to be fun. And so the goal of this project was to obtain a pristine sample of the asteroid Bennu and return it to Earth. Bennu is a very primitive asteroid. It has not been much processed since the beginning of the solar system. We know that from telescopic observations that it doesn't have any of the chemical signs of a lot of like igneous kinds of processing. It probably does have water has processed it, but it's not been melted or any of that. So construction of the spacecraft started in 2011, launched in 2016. We were at Bennu for about 2 years, working at Bennu for about 2 years, 2019, 2020. Left Bennu at May of 21. The sample came back last fall, and then, of course, now we're headed off to our next target, Apophis. So this is a somewhat cartoonish version of the spacecraft, this is the business end. This is the science deck. This big white thing in the middle is the sample return capsule. So that's what that's what we put the sample in. We have 2 spectrometers, a near-infrared spectrometer and a mid to thermal infrared spectrometer. We have 3 main science cameras. Right? They basically do just with different fields of view. One of them had color filters. We had 2 navigation cameras. We have and a few other cameras just looking at things. And there was an X-ray experiment. This was a student project to do X-ray characterization, and we have a laser ranger. So we have a lot of instruments on this spacecraft. So before we went to Bennu, what did we know about it? We knew that it was this primitive thing, primitive kind of asteroid, but we also, it was chosen in part because we had radar imagery. And so we also had a shape model based on that radar imagery. The sort of movie on the left is showing you some of the actual radar imagery. You can see that radar images, the ones Luisa showed you before, were some of them were very nice. This one is what we call a pretty good radar image. It's not the best, but it's pretty good. It's got hundreds of pixels, and you can see the basic shape of the asteroid rotating. Using this image, this image and a bunch more like it. This is just from one day. We were able to make this shape model, so we could see that it's a little under 500 meters across. It's basically a round ball with some lumpy things. It does have this one sort of mountain on it that's was tens of meters across. We know how fast it rotates. Rotates in 4.3 hours. We knew that it was the bulk density was about 1,200 kilograms per cubic meter. We knew that based on how it reacted to the solar basically the solar radiation forces. We could estimate the mass because we knew how big it was, and so we knew what the sail area was, so we could see how much force the solar radiation was putting on it. We did choose this target. There were several to choose from, and this target was chosen because we had these radar data, so we could do a lot more characterization ahead of time. There was one other choice, which was in fact Ryugu, the Japanese Hayabusa 2 target. But we said we're going to choose the one that we know more about. So again, this Luisa showed a very similar figure. What is radar? Did radar astronomy? What you do for radar astronomy is you use. So this was a 1 million watt transmitter at 2.38 gigahertz. We shine out radio waves for the round trip light time that it takes, right? The time it takes light to get out to the target and back. For Bennu, I think the shorter day, that was about 20 seconds, and the longer days, it was a couple of minutes. Those are typical numbers. Then it turn off the radar transmitter just as the signal's getting back, turn on the radar receiver, and receive signal for that same length of time. And as Luisa said, the power of this is that you can code the signal, which means that since you know exactly what you transmitted, you can correlate what you get back with what you transmitted, which is why you can do this imagery of things hundreds of, many millions of kilometers away. Sunlight is much brighter. We discover asteroids by looking at reflected sunlight because we don't know where they are. But if you do know mostly where things are, you can really find things up by using this coded signals. And as you said, right, the telescope collapsed in December 1st, 2020, and it's extremely unlikely at this point that it will be rebuilt there. So what do we measure? We measure positions and velocities, right? We measure, and by measuring, right, that's what a radar does. You measure how long the light takes to get there and back, and you measure a Doppler shift. So you measure position and velocity. So if you look at the orbit, that helps you improve the orbit. We knew where Bennu was to within about 2 kilometers at the time we arrived. But of course, and the objects, you can measure the distance basically from the front of the asteroid to the back of the asteroid. So that tells you things about its size and its shape. It has a rotational velocity. And by looking at the Doppler shift, you can measure that rotational velocity, touch about its spin, and but scattering properties can give you some estimates of surface roughness. That's actually quite difficult. And one of the important things about studying asteroids with radar is that it has a very different sampling bias than optical observations. We really only care how far away it is to know how bright it's going to be. We don't really care anything about what color it is or albedo or any of that. So it means for some things that we had, it's not unbiased, but it's differently biased. That helps us understand the population of asteroids. So again, this is a radar image, and it's chopped up in, you measure how far away the front of the asteroid is and how far away the back of the asteroid is, and you measure those separately. And you measure a Doppler shift and things, right? If something is rotating, then things on one side of the asteroid are moving faster than things on the other side, and so you chops it up into these up into pixels like this. You can imagine these images as if you were standing on the you're looking down from the North Pole and shining a flashlight from at the equator. That's sort of what these images look like, except of course you add the top half and the bottom half together. The north and south get added together. And I always forget that it does this. So on the left again, there is some of the radar data that was used in making the shape model. And on the right, you see the radar shape model. We published that in 2013. So as we approached Bennu in fall of 2018, I was a little nervous because I had, when people were asking me things about the model, I was telling them things and I said, wait a minute, I'm a scientist. In science, if your model is wrong, that just means you get to write a second paper about why it was wrong and what the right answer is. It's fine to be wrong, right? That's sort of the part of science is you figure things out and you start off by being wrong, and then you learn things and you're more right. And they said, wait a minute, you're building a spacecraft based on things I'm telling you. I'm going to go be much more careful about my uncertainties, and so. On the left here, we have, this is 2018, October and November. On the left here, this is the radar shape model, projected the way that it would be seen from the spacecraft. We were able to figure that out. And on the right are the first images that we took of asteroid Bennu. So, right, you can see the pixels, there's the first image. And then 2 days later, you can start to see some more features. And there's that boulder, that mountain. And by 4 days after that, the spacecraft image is clearly better than the radar model. And so my job is done. You can see that I didn't get this is twisted a little bit. So you can see that I didn't get the pole quite right. I was off by 6 degrees. That was 1.2 sigma. I was perfectly happy with that. The size is almost perfect. The real object is a little more sort of puffed out marshmallow than the asteroid, but it was great. It really helped us plan the mission. because we really knew where we were going. And so, right, so on the right is the model, and on the left is the images we took. So I'm bragging here. So here we are at Bennu. Now, one thing we did kind of predict about the model that wasn't right is it's really, really rough. It's covered in boulders. Partly what that is the radar has a 10-centimeter wavelength, so it's sensitive to sort of roughness at 10-centimeter scales. And we had 15-meter pixels, so we could see great big rocks, but we couldn't see 1-meter boulders. And so it turns out Bennu was covered in 1 to few meter boulders, which is going to get to be an issue in a minute, because the way the sampler works is it needs to find a fairly big flat spot that has a lot of dirt to go scoop up. And it was definitely a challenge finding that spot. Again, here's just another picture showing you how rough Bennu is. These rocks are several meters across, and it's really just a pile of rocks. There are some smoother regions. This is a particularly exciting one. So here's a map of Bennu, and you can see there are some smoother regions in some of these things that look like craters, and some extremely rough areas. This area over here, we called Boulder Town at the time. One of the things is that since this was a sample return mission, we were very much concentrating on the places that we could go to get a sample. And so a lot of the sort of studies that one would do of all of these things, any place like, oh, there's a lot of boulders, that's cool, but for right now, we're going to ignore that because it's a place we're definitely not going. And so we had to sort of, everybody wanted to go discuss the cool things. He said, no, we're trying to find a place to get a sample to bring home. Then we can talk about the cool thing. In the end, we chose this Hokioi crater up here. It was basically it had a smooth region, and when we got high resolution imaging, we ended up with some of our highest resolution images were less than a centimeter in pixel size. We were able to see that it actually had material that would fit in the sampler. The largest particles that go in the sampler was about 2.5 centimeters. And we definitely saw that there was rocks, sort of gravel of that size there. The names are all mythical birds from different cultures. And that's because Bennu itself is a bird. It's an Egyptian mythological bird. And so all of the names for features ended up being the names of mythical birds in different cultures, or bird-like creatures. Like Pegasus isn't really a bird, but it has wings. So this is the place we chose to go get our sample. The orange circle is the as-designed uncertainty for the tag site. The touch, we called it tag, touch, and go. So the orange circle is the original uncertainty spec that we gave the engineers. That clearly wasn't going to work because the crater that the material we could find was down here in this little parking lot. The parking lot is to scale, and we basically have to park our spacecraft in one of these spaces. The blue circle is the uncertainty circle we ended up with. I think that was a 99% uncertainty circle, 98 maybe. And so we were able to do, basically, we've done a lot of characterization of the spacecraft, and we also did some optical navigation improvements so that the spacecraft was able to autonomously do one correction to do the final aiming. And it also had basically a rejection threshold that said, when it got to 5 meters from the surface, if it didn't like what it saw, meaning it was not in the places we had said was safe, the spacecraft would back off and we would try again. In fact, we had no trouble. We ended up something like 3/4 of a meter from our target area, which is basically right there in the middle. We were able to get the sample. That was all cool. And so, right here, this is just a close-up of that. And so this is 4 millimeters per pixel. And so these rocks are small enough to be sampleable. Of course, there are still some that couldn't be, but we figured out that there was something like a 95% chance of getting a good sample in the first try, and less than a 2% chance of having actually, I think it was less than 0.2% chance of having a problem. And so this is going to be a movie. I hope it works through the Zoom of the actual sampling event. We're coming in towards Bennu. We're going to go flip off to the side, and that's because we originally planned to do it differently, and we just didn't want to change the sequence, so the sequence stayed the same. All right, now you can see this is the crater coming into view. This camera is looking off a little to the side, so you're going to see the sampler, the shadow of the sampler is going to appear, and then it's going to take the sample. There's the shadow of the sampler, and then kablooey. So what the sampler is, I'm going to show it in a second. The sampler is basically an old-fashioned, it looks like an old-fashioned car air filter. It's round, it's about a foot across, and that's really how it works. It's a vacuum cleaner, except of course we have the vacuum in space, so we had to bring our own air. We brought 3 bottles of nitrogen, basically just lecture bottles, and then when we touched the surface, we blew the nitrogen onto the surface, and it blew material up into the sampler, and where it was captured. And we're close enough. We'll watch this one more time. Here we come in again. There's the sampler and kablooey. So here's the other camera is now showing you the actual. It's showing the sample, and it's actually taking the sample, and you can see it disturbing the surface there. And one of these things, right, this is microgravity. The object's 500 meters across. Escape velocity is 20 centimeters a second. Just our human intuition of how materials work in those environments is really, our intuition is just wrong. And it's very difficult to make it right, even when we know it's true. We do a lot of computer modeling, and we can usually those usually work pretty well because we can put in all those things and make it work. But for example, you can see that when the sampler, again, is about a foot across, it's moving 10 centimeters a second, and it's disturbing this rock up here. Right? You can see it moves. So this is the last frame before we touched and the first frame after we touch. And of course, 1 second later, we blow that bottle of nitrogen, and then this camera is just full of rocks, so you can't see anything. So the surface is really porous, and but it worked. We got our sample. Here it is again. Here's where you can really see that this looks like exactly like a car air filter, and we're putting the sample in the sample return capsule and closing it up and coming home. And then here we are 2 years later. There's the sample return capsule sitting on the desert in Utah. It was very exciting. We did actually have a problem with one of the parachutes, but it turned out it was fine. And so when we saw the big orange and white parachute open, we were all very happy. Landed right here in the desert in Utah, and then this is Dante Loretta. He is the PI of the OSIRIS-REx mission, there to go and pick up his capsule. This is Scott Sanford and Francis McCubbin. He's the he's the curation lead at Johnson Space Flight Center, and so he's the one responsible for it now. It is being moved to Johnson Space Flight Center, and so for reasons I still don't understand, they said the best way to do it is to wrap it up in a plastic bag, stick it at the end of a long piece of line, and fly it in a helicopter to the initial processing facility, which was basically, this is at the Dugway Proving Ground. So they made a little mini lab, and they just, and of course it landed in the middle of the desert, and they flew it there. Why this was the best way to move it, I have no idea, but we were repeatedly assured that it was the right way. So it got boxed up. And my favorite part about this picture is this says important space equipment or something like that. And you can see that this label is faded. Every one of these samplers has been brought back in this same box for the last like 15 years. The green one here I like just because I don't know why it's green. Nobody knows why it's green, but it reminds me of the picture in Raiders of the Lost Ark where the top men are putting the box in their warehouse. It was flown then to Houston. And I like this one too, up in Utah, but we had these mission shirts and we were wearing hard hats and this and that. And we get to Houston and it's blue jeans and sea caps, just because Texas is different from other places. That was just one of those cultural things. So here it is at Johnson Space Center being opened. Again, you can see the air filter. You can see this dirt here. So it was a subject to 30 Gs of deceleration. So obviously things are going to get shaken around, and so some of the dirt ended up just out in the out in the container. It's probably at the edge because they were blowing that as soon as it got to the ground, they were blowing nitrogen on it to keep it clean, and that probably just spread some of that material out. And so here's Bennu. This bolt head is about 1 centimeter across, and so these little rocks are bigger than 1 centimeter. We got our requirement was 60 grams. We had pulled out 70 grams by about a month later. You may have heard the story about the stuck bolts. There were 2 bolts that they couldn't open, possibly cold welded, and people said, "Oh, you didn't do it right." I said, "Yes, we did." The biggest thing about this mission was trying to bring back a very pristine sample. And so we didn't, wherever possible, we didn't use lubricants. We didn't use, it said, if we need to saw this open, that's okay. We don't want to contaminate it. So we don't want to use any plastic. We don't want to use anything one that could come loose, but better that it be stuck closed and not than to come undone. And also not contaminating it. So we ended up with these 2 stuck bolts. Am I still on? Something just changed. Looks okay. So possibly cold welded, but that's fine. We got our 70 grams out. And then basically here you can see the issue. These people are working with gloves in a glove box. There's no clearance. So there was no way to get leverage with a screwdriver very well. So what they did, once they said, okay, I need to get that bolt out, is they just built the screwdriver with a clamp on it to hold the thing in the right place. It took about 2 months to do that because they needed to make sure they used the right kind of materials. So it just took a while, but nobody was in a hurry at this point. They already had their 70 grams. They were already doing their initial analyses with the amount we were supposed to get, and we got this done. So this is really why. If you could, there was no way to get up there and push on it like you would with like you normally would if you were at your home or in your shop. Okay, and so I think this is really fun. On the left is the very first image of Bennu I took in 1999 in September. And here I am holding a sample of Bennu in the lab. And I don't actually get to touch it. It's in a vial under nitrogen. It's all very clean. But it's not many astronomers get to get this close to their samples. So after we dropped off the sample return capsule, the spacecraft diverted so it wouldn't hit the Earth. So we have this spacecraft. The X-ray spectrometer has died. Basically, they have a very finite lifetime in space due to cosmic rays. It basically just destroys the detector. That's expected and fine. The sample return capsule is gone. That's good. But we have this spacecraft with a bunch of other instruments on it. Oh, I should say one more thing. So, and on last Wednesday, they published the first paper discussing the first initial results from the Bennu sample analysis. And in fact, they found some materials on this asteroid on Bennu that do not appear in any meteorites, right? So, and Bennu is clearly very fragile, and we think basically objects like Bennu, you don't get many meteorites from them because they don't survive entering the atmosphere. They would disintegrate if they enter the atmosphere. So there's some materials that we're seeing that haven't been seen on meteorites, and that's going to help us again, mainly with this understanding of the origin of the solar system. What are we really made of, and where do the materials that form the planets come from? All right, but now, so we don't have a sampler, so we're not going to do sample return. But we do have a spacecraft that's perfectly good. And so we're going to send it to another asteroid, Apophis. We're going to arrive at Apophis in June of 2029. That date is mainly set by the fact that, so we have something like 500 meters a second of fuel, or we did at the end of the, after we left, dropped the sample off. And the typical delta V between asteroids is something like 5 kilometers a second. And so We don't have that much fuel. So, but we do have the Earth. So we're going to have to use 3 Earth gravity assists to change our orbit to go to another asteroid. And that makes sense because if you want to think about where something is, it has a position and it has a velocity. There are 6 numbers that determine an orbit, right? There's 6 orbital elements, 3 positions and 3 velocities. It's one way to think about it. Well, if you go past, if you have Earth's gravity move you, you have 2 things you can adjust. You can adjust where you are facing the Earth, which direction, and you can adjust how far away you go. So you basically can adjust 2 things. So if you need to change 6 numbers and you adjust 2 each time, you got to do it 3 times. And so that's essentially, we have to do 3 Earth gravity assists, and that's what takes this 6 years. And so we'll part of Apophis in June of 2029. Now, you may have heard of Apophis. Apophis is going to come extremely close to the Earth. It's 30,000 kilometers away, lower than geosynchronous satellites. And it arrives on April 13th, 2029. And we arrive 1 hour behind it. And we're going to use that last Earth gravity assist. We're going to meet up with Apophis and continue on. And so when Apophis was discovered, there was some concern that it would hit the Earth in 2029. And the unusual part about that story, usually you discover one of these things, you don't know where it is very well because you just have a few measurements. You say, oh, it has a 0.5% of hitting the Earth at some time. But then you go make another measurement, and usually what happens is that those odds go down because I now know better where it is. This is one of the few where after the second measurement went up to 4%. And the odds actually increased. Said, oh, that's not good. But eventually, yes, it's not. Apophis is not going to hit the Earth. It's not going to hit the Earth. It's not going to hit the Earth in 2029. So, but we're going to go sail along with it and meet up with it. And basically, now this is a science investigation, right? We're not bringing we don't have a way to bring a sample back, so we're just going to study as much about it as we can. It's going to be, right, we're 500 meters a second. We have this great spacecraft. We were trying to, people said, well, can you do a flyby? It's not a flyby instrument, right? The spacecraft was designed to get up close and personal and look real carefully at the whole thing. And so that's what we're going to do. Apophis, as I said, Apophis is an exciting object because it's a fairly large object. It's about 350 meters across, and it comes very close to the Earth, where these size of these dots is how big the object is, and it's just how close to the Earth do they get. Apophis is sort of the largest object that comes really close for quite a while. It's sort of a 1 in 7,500 year kind of object event that something that big comes that close. It's close enough that the orbit will definitely be changed. The rotation state will also definitely be changed by just tidal forces. And another thing that happens is as soon as the people with the telescopes, as soon as it gets to close approach, it's going to go right to where the sun is, and people aren't going to be able to see it anymore. So we're going to go follow it and see what we can learn about Apophis. Right now, what do we know about Apophis? We know its orbit. We know about how big it is, and we don't know much else. Except we do know that it's much brighter. Bennu is 4% albedo, is dark as charcoal. This is 30% albedo, which is a fairly typical rock you would find outside. Its spectrum is quite different. It is a very processed stony object. It's not pristine in any way. It's been heavily processed out in the solar system. It's actually the most common kind of asteroid. And so if we are worried of things about hazards, it's the one most likely to be the one that comes and gets us, just because that's the one there's the most of. So it's a little tricky because, again, the spacecraft were designed specifically for Bennu. So we're having a bit of a problem that since it's so much brighter, we're going to have to figure out how to make we can't take an exposure as short as we would really like to. So we're going to have to be fairly creative. And chemistry-wise, these stony objects are much easier to characterize. And we'll actually learn a lot more about them than we did with Bennu, chemistry-wise, just because there's just a lot more to see. And we don't have the sampler. But so what we're going to do is take pictures of all over the asteroid, and then we want to go look underneath the surface. Say, well, at Apophis, here, this thing on the right here is topography. The blue spots are deep, and the red spots are high. When we went and got the sample of Apophis, right, the sample had this big bottle of nitrogen, made an explosion that dug a hole. But if you look out here, where the thrusters are, there are also smaller holes. So the thrusters actually also dug holes. So what I think we'll be able to do is go down towards the surface. Once we've made all our measurements, we'll go down towards the surface, blow holes in it, and then go take pictures again. And we'll be able to see underneath the surface and see if this object is right. If Apophis is that sort of friable, easy to move around material like Bennu was, or if it's sturdier, or just what about it? So that's what we're going to do. We will still be able to interact with the surface, even though we don't have the sampler. One trick, again, we have to use Earth gravity assist to get us to Apophis because we don't have enough fuel otherwise. So the spacecraft that dropped off the sample, it says EGA 0. We dropped off the sample there. That was the divert maneuver from last September. But the orbit we're on, we have to go. We go 3 times around, have a gravity assist, go over to the other side, have another gravity assist, go 3 times around again, and then finally meet up with Apophis on our 3rd gravity assist in 2029. One thing that you can see here, though, is here's the sun. The dotted line is the orbit of the Earth. So we get to the spacecraft gets to half an AU, halfway to the sun. The spacecraft was not designed to get that close to the sun. Because we knew it was going to end up on this orbit, but we didn't really care when building the original spacecraft. Well, so it gets really hot as you get close to the sun, of course, and so we had to come up with a special way to that the spacecraft. The instruments you can face some parts away from the sun, but something has to be facing it, right? And so the instruments are on this side, but a lot of the spacecraft sort of navigation guts are down on this side, and we need to protect those from the sun. The things like hydrazine lines and the guidance sensors and the gyros, all that stuff. So what we're going to do is use the solar panel to just cover up the parts that we are concerned about. We call this the fig leaf mode because it covers up the important bits. And we spend about 6 weeks in each, actually closer to 10 weeks in each of the visits to do that. We have done our first one. We've had our first perihelion. We're right about here now. We've been around once and we're right about here. Actually, maybe close to there. And the spacecraft did fine. All that stuff worked. We learned some things. There were a few little weirdnesses, but nothing bad happened. And in fact, it turns out that one of the cameras has some radiation damage just from being in space. And it turns out that one of the ways you cure radiation damage is you just gently heat the detector and let it cool off again. Well, it got heated up to about 50 degrees C. And in fact, a lot of the radiation damage went away. So that's good. Now, whether good once and good 6 times aren't necessarily the same thing. So we'll see how that goes. So, right. So I should have this isn't the current one. Like I said, we're about here. We're on our way. We're gonna arrive in. I lost my mouse. There we go. We're going to. Yeah. So here we are in 2022 and 2024. We have a whole bunch of EGAs and perihelia that to get there. Some deep space maneuvers. When we arrive at Apophis, we arrive in April. This is now 2029. We arrive in April 2029. It takes us about 6 weeks to actually go get to the asteroid. We arrive we're about an hour behind going past the Earth, but because of the uncertainties, we don't want to be too close at that point because nothing's quite sure of the positions aren't that perfect. So, and we want to approach slowly. So it's going to take us about 6 weeks to actually get to Apophis, where get to means like 10 kilometers away, where we can really use our cameras and take good pictures. We have various surveys. We have triangle survey, we're just sort of bopping around, station keeping, taking pictures from about 15 kilometers away to get our shape model, figure out the rotation. Then we have to go measure the gravity, so we go close just to see what the mass is. We're going to go into orbit. We have a LiDAR, and the LiDAR likes to be in orbit, so it's going to go be in orbit around to take to do the shape model with the LiDAR. Then we have what we're calling the starfish surveys. That's just based on the pattern. It's like a hexagonal pattern, and that's where we do most of our spectroscopy. Do a few things like that. We're going to choose a couple of sites to go study in greater detail. We'll go up closer to those sites, take some pictures, and then we're going to go. This STIR is what we're calling this thing where we go and disturb the surface. We've had a very hard time coming with a good acronym, but that's the one we're at now. It has to have a cool acronym, and it just doesn't seem quite cool enough, but we're working on it. And then we have this marked as mission closeout. That's for writing papers. Assuming that the spacecraft is still in good shape, we will almost certainly propose to do an extended mission. This is a very cost constrained. All extended missions are very cost constrained, but to some extent, if you still have things to do, you can ask for a little more money because you've done most of the work getting there. Let's see if we can do a little. Now that we know it all works, let's see what else could we do for just a little more. And so hopefully we think it's probably worth doing about another 6 months to a year of work and before we've really done everything we can do. And so that's I guess that's the end of my presentation, and I'll take any questions. I see there are a bunch of questions. I couldn't really do them in the fly here. Control. Okay, so for how do we get there, for OSIRIS-REx, we did everything ground in the loop. We did everything slowly, and our standard observation would be we would go take one 5-hour observation. Bennu rotated in 4.3 hours, so we would observe for 5 hours and watch the whole thing go around. And so each observation would be different, but one day we would go look from a particular direction and take pictures of it as it moved around. So with that, we could do it all ground in the loop. What we could do is we could design, we could take a lot of imagery to figure out where we were, design the orbit. We would do, take one last navigation image a day before we want to do the observation, update the solution and tell the spacecraft, do this. And it was always good enough, except the one time when it snowed, when there was a freak blizzard and we weren't able to do it, uplink our final map. For Apophis, we may not be able to do that because it's a very different observing scheme. We have to observe basically every few hours for a month, and there's no way people can be involved in that. So we're working on how it is we're going to deal with that. A kind of propagation model. I kind of know what you mean by that, but these people have been doing this a long time. I'm not an astronavigator. I don't literally know what people do as far as with integrators or anything like that. Okay, so we could hyperspectral imagers are, so our spectrometers are very wide band, but they're single pixel, and that is a thing that maybe we wish we hadn't done. If there's one thing I would have liked, it would have been a thermal imager. The biggest thing about spacecraft instruments, though, is you want them to be simple, because there's just a whole lot of work in making things go. And so, as an example, our thermal spectrometer has two modes, off and on. And you try to say, take data, and it takes data, and it takes 8 kilobytes every 2 seconds. When the student instrument, they had all these calibrations they had to do. So anytime they wanted to observe, they said, we need this, but this, turn the spacecraft this way, do that. And we said, no, I'm sorry, that's too complicated right now. If we could just take data, that would be easy. But if I have to go and do a bunch of stuff, I can't do that right now. So any concern with like complicated instruments becomes tricky, just because it turns out to be really helpful to have operation be simple. So, but something like a prism with You can have those kinds of spectral imagers, like you might have a push broom kind of spectrometer where you had an array of pixels in one direction, spectra in the other direction going onto a detector, and then you move across the object to get the third direction. That's a thing that we can definitely do, and we might. I think that would be valuable, and again, particularly it would have been nice to have higher spatial resolution on the spectrometers than we ended up with.
Hey, Mike, we had a little technical glitch here and missed your answer to the previous question. Could you just repeat it briefly?
Well, there was the one about the propagation model, and I don't know how. I mean, the math that we use. I'm not an astronavigator. Is that the one?
The first question.
The first question. Oh, control. So for the control, it turns out, I'll just do the whole thing again if that's okay. So Bennu rotates in 4.3 hours. Our standard observing was we would watch it for 5, and we would do that once a week. Right? We would get into whatever geometry we wanted and observe for 5 hours once a week. So we did that all ground in the loop. We would set everything up, and then the day before, get a couple last navigation images, and as long as we did that, and upload a final ephemeris and just tell the spacecraft where to go. So there wasn't so much control. There was no onboard control that had to happen. It was all done it was all pre-planned. I mean, there are classical controllers like this. The gyros and the sun sensors are standard, PID loops, but the way we did that planning was all ground in the loop.
Thank you. Any questions from the audience here on site? One question. Can you come around here? We have a question on site, Mike.
Hi, Dr. Nolan. First of all, thank you so much for your wonderful presentation. Learned a lot. I caught you added one comment regarding your camera sensor, and it was quite a shock to me that this is the case. But you mentioned that your camera sensor had radiation damage, but it was cured by heating the camera sensor to 50 degrees C. Could you elaborate more on that? And was it more radiation damage on the sensor? And was it like a CMOS sensor, or what kind of imager?
I think it's a CMOS sensor, and yeah, I mean, there's cosmic rays in space. It happens all the time, right? That you get hot bad pixels. If you look at Hubble image, if you look at an actual image from Hubble, it's covered in cosmic rays, and that one of the ways some of those will anneal out if you heat it a little bit. Now, we didn't intend to heat it, but in the end. But we did as part of this getting close to the sun, and it turns out that did anneal out some of these hot pixels. The details of that I don't know.
Thank you.
Thank you. Yeah,
Question from the remote audience?
One I guess a follow-up question was that done when it was operational, or was the imager off?
We did not purposely heat it. We just got close to the sun, and we kept everything as cold as we could. And it turns out for that particular detector, 50C was as cold as we could keep it. And Brent says, right, it's an N-body integrator. And it does have, includes Yarkovsky effect. It includes pointing Robertson drag. It includes relativity. It includes all those things, but it's just a standard N-body integrator. With a lot of bells and whistles.
Thank you, Mike. So currently you are after the first heliocentric flyby, 5 more to go?
Yep. The next one is in September.
September. Okay. We are holding our fingers for success there. I think we are ready to move to the next talk. Wonderful talk, Mike. Always fascinating to hear you talk about those things. And we are looking forward to seeing more talks about Profis now. Thank you for joining us today. And I think the next person is Brent Barbee from NASA Goddard. Are you online, Brent?
Yes, I'm here, Nahum. Can you hear my audio?
Yes, we can hear your audio loud and clear. And
All
we
right.
are into your video in just one moment here.
Okay.
And if you could introduce yourself instead of me reading the bio for you, if you could just talk a little bit about yourself. Okay, yeah, now we are on and you can start, Brent. Thank you.
Okay, great. Thanks, Nahum. My name is Brent Barbee. I'm an aerospace engineer at the NASA Goddard Space Flight Center. And I'm also an adjunct professor at the University of Maryland's Aerospace Engineering Department. My work centers on planetary defense against hazardous asteroids and comets. As Mike explained to you during his talk about OSIRIS-REx, planetary defense is part of the reason why we study asteroids, but of course there's a lot of fundamental science reasons why we study them too. And so today I'm going to be talking to you about a mission that I worked on called DART. I'll bring up some presentation slides here in a second. Share my screen. Okay, are you able to see my presentation, Nahum?
Yes. Yes, we can see it loud and clear.
Okay, how about now?
Yeah, please proceed.
Okay.
Do you want to put your presentation in slide mode, maybe?
I did. Is it showing up as slideshow mode for you?
Oh, is it okay? Yeah, I think the others can. It's not?
Yeah, it's you have to click on the screen.
Yeah,
You need to share the full screen one, not this one.
You need to share the full screen on your side, not the one with the PowerPoint. We see the PowerPoint and yeah, you need to switch around.
All right, give me a sec. I think I understand what you mean. All right, how's that?
Yep, perfect.
Great. Okay, so today I'm going to talk to you about planetary defense and NASA's Double Asteroid Redirection Test, or DART mission. As my friend Mike told you, we always have to have a good acronym, and I think DART's a pretty good one. I'll also point out that DART was humankind's very first planetary defense test and demonstration mission, which makes it very special. All right, so if we're defending against something, there must be a hazard or a threat out there to defend against. And in fact, we have a large population of near-Earth asteroids orbiting around the sun in the inner solar system. And some of these asteroids have orbits that cross or closely approach the orbit of the Earth. And that raises the possibility of these asteroids actually colliding with our planet at various times. And the population of asteroids, in terms of the sizes of the asteroids, follows roughly what we call a power law, which means that the small objects are exponentially more numerous than the big ones, which is a good thing for us because it means that we're less likely on any given day to be struck by a very large asteroid. But because we haven't finished cataloging the entire population, we don't know where all of them are. And so there's a chance that we could get struck by something or discover something that's on its way to hit us. And so we're motivated to be prepared to stop it. Now we get hit by small stuff that's several meters in size a couple times a year. Things that are maybe a couple tens of meters in size might hit us, once or twice a century. And then when we get to things that are a couple 100 meters in size, fortunately, those impacts we think are less frequent. The average frequency might be in the tens of thousands of years. And then things that, the size of what took out the dinosaurs, maybe like, 10,000 meters wide. We think that those impacts occur maybe every, 100 to 200 million years. But these are all average intervals. Because we haven't discovered everything, the next big one could, be discovered tomorrow and be on its way to hit us in 10 years. We just don't know. So we're motivated to find the ones we haven't found yet and then develop techniques and capabilities to stop them. An example of a very well-known crater here on Earth is the so-called Barringer meteor crater in Arizona. And this was made about 50,000 years ago by a 50-meter diameter metallic asteroid. It's a 1,200-meter wide crater. It's about 180 meters deep. And that, 50-meter metallic asteroid, released enough energy to cause big fireball out to tens of about 10 kilometers, and then created enough energy and a big enough pressure wave to cause significant devastation out to several tens of kilometers away from the impact site. And if we overlay this on Washington, D.C., we can see that just the fireball alone would have easily taken out D.C. and caused a lot of damage throughout Maryland. This graph here shows our recordings of small asteroid impacts creating fireballs up in the upper atmosphere all around the Earth, going back to 1988 up to present day. And that big red one that you can see there in the upper right was an impactor called Chelyabinsk. It's about 20 meters wide, so we think. It released about 0.5 megaton of energy, and it caused about $33 million worth of damage in the city of Chelyabinsk, Russia. 1,600 people were injured. Nobody was killed, fortunately. It hit our atmosphere February 15th, 2013, so a little over 11 years ago. And so, ever since the Alvarez hypothesis was published back in 1980, we've been keenly aware of the need to defend ourselves from this kind of threat, but it took a few decades after that for the science and the understanding to really catch up to that initial realization that a large impact 66 million years ago made the dinosaurs and 75% of everything else living at the time extinct. But by 2010, the National Academies had published a report called Defending Planet Earth, and noted that the first priority for a space mission in the mitigation area is an experimental test of a so-called kinetic impactor. So there are multiple techniques for stopping an incoming asteroid. I'm not going to go into all the details of them now, but you can ask me about them later if there's time. But briefly, there are gravity tractors, ion beam deflection systems, nuclear devices can be used to great effect to deflect or destroy asteroids. And then there's kinetic impactors, which are perhaps the simplest technology. You just ram a spacecraft into the asteroid at really high speed, and the momentum of the spacecraft changes the momentum of the asteroid. And then importantly, the material that gets kicked off the asteroid by the spacecraft impact also carries momentum and can change the asteroid's momentum even more than the spacecraft could by itself. And this extra momentum enhancement factor from the debris kicked off the asteroid was one of the very important things that we wanted to measure with our DART spacecraft experiment. So we conceived DART as a good fit for testing the kinetic impactor. And in the years since, planetary defense has been recognized by the technical community as a applied planetary science. And for the first time, a chapter about planetary defense was included in our decadal survey report for planetary science and astrobiology, published very recently, back in 2022. And so DART serves as our very first test of any asteroid deflection system, and it's going to be a kinetic impactor demonstration. At NASA, we have a planetary defense coordination office where we do search, detection, tracking for asteroids, characterize them, plan and coordinate efforts both within the US government and internationally, assess the orbits and the potential for these objects to impact the Earth, and also develop plans and techniques to mitigate the threat, including techniques to deflect or destroy the asteroids if we should be called upon to do so. And DART was one of our key activities in the mitigation area. At the White House level in the United States, we also have a National Preparedness Strategy and Action Plan for near-Earth object hazards and planetary defense. Our DART mission chiefly helped us out with goal number 3 in that strategy and action plan, which is to become better prepared to reconnoiter, deflect, and if necessary, disrupt asteroids. But the science that went into DART also helped us with detection and tracking, modeling, and international cooperation. So the asteroid that we selected for the DART experiment is called Didymos. It was discovered back in 1996, and you can see in this image here, there's a little blue bracket around where Didymos is moving in the sky. Didymos is about 780 meters wide. So it's somewhat bigger than the asteroid Bennu that you heard about from Mike. And Didymos is a binary asteroid. And this was one of the reasons why we chose it for the DART experiment. The secondary object that's orbiting Didymos is called Dimorphos, and you can see it over there next to the Great Pyramid of Giza, which it's comparable in size with. And the reason we chose a binary asteroid is because for a relatively modest sized spacecraft and a relatively reasonable impact speed, we could create a big enough change in the orbit of the little asteroid around the big asteroid that we could measure that change. Whereas if you're going to be changing the orbit of an asteroid like Didymos, or even an asteroid the size of Dimorphos that's orbiting the sun all by itself, you need a lot more push in order to make a change in the asteroid's orbit around the sun that's measurable. But making a change in the small asteroid's orbit around the bigger asteroid's orbit, that can be done with a lot less energy. And so we could design a very affordable and very cost-effective experiment to change the mutual orbit of the binary asteroid system. This is our DART spacecraft. Each solar array wing is about 28 feet long. The spacecraft to which the wings are attached is about the size of a refrigerator. The main instrument on DART was called Draco, which was our camera that we used to target the asteroid. And we also carried a CubeSat called Licia Cube, which was provided by the Italian Space Agency. And we ejected Licia Cube about 10 days before we struck the asteroid, so that Licia Cube could take photos of what was happening, because of course the DART spacecraft itself is going to be sending back all the images it can, but it's going to be destroyed by the impact. The original plan back when DART was first conceived in the early 2010s was to have the European Space Agency provide a rendezvous observer that would get to Didymos first and be on hand to watch everything happen. But that didn't come to pass in Europe. And so they said, well, look, we can provide Licia Cube. And then afterwards they said, okay, actually in 2024, we can launch a mission called Hera that's going to go rendezvous with the Didymos system after the fact, arriving in 2026, and do a post hoc characterization of the binary asteroid system. And that's going to be done, the spacecraft's going to be launching in October of 2024. We'll talk a little bit more about that later. So this diagram here summarizes the mission plan. We launched in November of 2021. We struck the asteroid about 10 months later in late September of 2022. The DART spacecraft was about 580 kilograms at impact, coming in at about 6.1 kilometers per second, which is about 14,000 miles per hour. Licia Cube was ejected before we struck, so it could collect imagery before, during, and after. And we organized this experiment to take place when the Didymos and Dimorphos binary asteroid system happened to be relatively close to the Earth, only 7 million miles away, which is a really, really short distance in astronomical terms. And by organizing the mission that way, that meant that all of our Earth-based telescopes, including the Hubble Space Telescope, would be able to collect a lot of data about what was going on. And so even though we didn't have a rendezvous observer spacecraft there, which would have been our preference, the experiment was designed so that we could still close the loop and figure out enough of what happened using telescopes on Earth. Our level 1 requirements for the DART mission were, number 1, to impact Dimorphos. So this was the fastest intercept of the asteroid as small as Dimorphos. It's a very challenging guidance, navigation, and control problem. So we want to demonstrate the capability to do that kind of high performance intercept of an asteroid. We wanted to cause at least a 73-second change in the asteroid's orbit period. And we wanted to measure that period change to within about 7.3 seconds accuracy using our ground-based observations. And then 4, as I mentioned previously, we wanted to measure and characterize the so-called beta factor. Beta is the momentum enhancement factor, and that's just because the Greek letter beta is used to denote that term in the overall equation for how much the asteroid's momentum is changed by the impact. And I'll talk more about that later. Here's an image of the DART spacecraft ready for its pre-ship inspection in September of 2021. You can see the solar arrays are all rolled up. And then after that was done, it was loaded onto a truck and driven out to Vandenberg Space Force Base. It was loaded into the nose cone of a Falcon 9 rocket. And then on November 24th, 2021 at 1:21 in the morning, Eastern Standard Time, the spacecraft launched on its Falcon 9 out of Vandenberg Space Force Base. It was a very spectacular night launch. I was there to see it along with a lot of the other folks who were working on the project. And this animation here shows what happened after launch. So you can see the Earth going around the sun on its orbit. That's the blue line. And then Didymos is on its larger orbit around the sun. It's larger and more elliptical orbit. The DART spacecraft launched into a somewhat Earth-like orbit in November of 2021. And then it cruised around the sun for about 10 months. And then you can see that we timed all of this so that the DART spacecraft would hit Dimorphos when the Didymos Dimorphos system was, as I said before, close to the Earth. And that enabled us to use our ground-based telescopes to see what was going on. And this animation here shows what happened in the Didymos system itself. So we had already measured using ground-based telescopes the orbital period of Dimorphos around Didymos. It was about 11 hours and 55 minutes. So we already knew that going into this. Then here comes the DART spacecraft. It ejects Licia Cube. DART goes in and hits Dimorphos. Licia Cube flies by. And now, because of the change in Dimorphos's momentum, it is now placed onto a new modified orbit around Didymos. And we were able to measure that the post-impact orbital period was 11 hours and 22 minutes. That's 33 minutes worth of period change, which is much, much bigger than the mere 73-second orbit period that was our minimum success criterion. So we were really, really excited about this result. The spacecraft's onboard camera Draco first detected Didymos about 2 months before impact. You can see an image of that there. And then the autonomous navigation system in the spacecraft's onboard computer became active 4 hours before impact, at which point we were 90,000 kilometers away. The spacecraft was built at the Johns Hopkins Applied Physics Laboratory right here in Maryland. And APL's software that was put on the spacecraft's onboard computer is called SmartNav. And it was, at this point, it took over control of the spacecraft because the speed of light limits the outbound and inbound signal transmission time. And so there's no way to joystick the spacecraft on the ground in the Mission Ops Center. That's impossible. The spacecraft must do all the calculations to fire its thrusters during the final sequence on board. And then this here shows what that looks like. So we've got, these are the images that were collected by the spacecraft's cameras. You can see the telemetry that was used by the targeting algorithm is overlaid. The green circle there is being drawn around Dimorphos, which the spacecraft's onboard computer was programmed to lock onto. This is overall showing the final 5 minutes to impact. And so this is faster than real time. But here in a minute, we're going to switch over to real time for the last few frames. This is real time imagery. And then that partial image was our first indication that we had successfully struck the target and the spacecraft had been destroyed. Meanwhile, Licia Cube was buzzing by and collecting images. This is one of the more striking ones. Absolutely gorgeous imagery. The sunlight reflecting off all of the debris created by the impact is really striking. Here in the lower part of this image, you can get a good view of the debris or ejecta plume coming off of the smaller asteroid Dimorphos. And then this is a composite image in which the frames around the asteroid are all at different contrast levels, which allow us to see some of the finer structure inside the debris plumes. This image was a mosaic created from the final 10 images from Draco. The theme for our naming of natural features on the asteroid is percussion musical instruments. And so each of these is a percussion musical instrument that you see marked there on the asteroid. And it's between Badaron and Atabek that the spacecraft struck. So we were able to reconstruct not only the shape and size and volume of Dimorphos and count boulders on its surface and select some features for naming. We were also able to, from the spacecraft's final telemetry, reconstruct exactly where it struck the asteroid within about 25 meters from the center of figure. And it landed between these two features shown here. And this is a three-dimensional rendering of our reconstruction of the impact geometry. Meanwhile, while LishaCube was sending back all of its images, and while we were studying the telemetry from DART's onboard computer and the images collected by the Draco camera, this worldwide network of ground-based observers was busy collecting lots and lots of imagery and data from the impact experiment, far more than I have time to show you here. But I just want to show you this map to give you a sense of scale. This was a truly worldwide effort. And it included assets in space such as HST, the Hubble Space Telescope, the James Webb Space Telescope, and even our Lucy spacecraft, which is another NASA asteroid exploration mission, was able to point its camera at Didymos and take some pictures. So starting the morning of September 27th, our team, shown here, this is our DART investigation team. So you've seen some folks here in person at APL, and then a lot of folks online on Zoom. This is a very international team, a lot of us from the US, plus a lot of our colleagues overseas. Starting the very next morning, September 27th, we were in the Science Operations Center at APL, just cranking away on this data for months, for the entire fall semester, working to get publications out, including for the AGU conference that was taking place in December. And this is from one of our larger in-person meetings where people around the US actually flew in November 9th, 44 days after impact. Now here's some of the images that we were getting from the ground-based telescopes. And this is an image of the impact event itself that's animated on the right-hand side. You can see a big puff of stuff coming off the asteroid right after the spacecraft hit. These are images from Hubble and the James Webb Space Telescope 5 hours after impact. Here is a Hubble image 12 days after impact. Hubble was a real powerhouse for us, collecting a lot of really important data about the geometry of the ejecta plume, which was really important for our calculations of that momentum enhancement factor. So that was really important. So the Hubble data and the LishaCube data were really key for us to be able to reconstruct the geometry of that ejecta plume so that we could calculate how much momentum it was carrying. That was one of our key goals. And because of the binary asteroid gravitational dynamics, you get some interesting features here. For example, you can see that this is a bifurcated tail. There's actually sort of, two lobes to the tail, which is very interesting. And the tail was just as visible from ground-based telescopes. This is 52 days post-impact. So really, this was sort of a man-made comet. We gave the asteroid a tail, and the tail persisted for quite a long time. This is a Hubble image 83 days post-impact. And then this sequence of images goes out to 155 days post-impact. So this is taking us through November, December, the end of December, and into January, and then into March. And the tail's getting faint, but you can still see it. And then even all the way out to 282 days post-impact, early July of the following year, 2023, you can still see the plume. So what did we do with all this data scientifically? Well, one of the things we did was we looked at changes in the apparent brightness of the Didymos binary system as seen in telescopes. And you can see that as the little asteroid that we struck, Dimorphos, goes around the asteroid, it casts shadows, and it also gets shadowed by Didymos. And so we look at the timing of these changes in brightness, and from that we can deduce the orbital period. That is how long Dimorphos takes to go around Didymos. And we're able to do this both before and after the impact, which allows us to figure out how much we changed the period of Dimorphos's orbit. We also had data from NASA's Goldstone Planetary Radar out in California. It's a big 70-meter radar dish. And so these are the radar images of Didymos and Dimorphos in early October. The yellow box is showing you where Didymos is, the bigger asteroid. And then the little green circle there shows you where Dimorphos is. And from the radar tracking, we were able to figure out where the orbital path of Dimorphos is. And the sort of teal colored circle shows you where Dimorphos would have been if we hadn't struck it. And then the green circles show you where Dimorphos actually was. And so by comparing these data, we were able to have an independent way of assessing how much we changed the period of Dimorphos's orbit. So all of this was combined with the data from the telescopic observations. Now, depending on how much material gets kicked off the asteroid, the asteroid might experience sort of the minimum push you would expect from only the spacecraft's momentum. But if you get a moderate amount of ejecta coming off the asteroid, it's going to get more of a push. And if you have lots of ejecta coming off the asteroid, it's going to get an even bigger push. And this is one of the key things we wanted to measure. And so this was one of my primary jobs on the scientific investigation team was to do that analysis. And so the data that we came up with is shown in the graph here on the left-hand side. And so I fit some curves to the data and came up with an average value of 3.6. And so that means that the momentum carried by the ejecta coming off the asteroid was roughly 3.5 times the amount of momentum that the spacecraft itself was carrying when it struck the asteroid. Now, remember, we didn't have a rendezvous observer at the asteroid before we hit it with DART. So even though we know the total mass of Didymos and Dimorphos together, we don't know exactly how much mass is in Didymos and how much mass is in Dimorphos. We know the shapes of those two bodies reasonably well, so we know their volumes. And so what that means is that the missing piece of information is the individual densities of the two asteroids. And so that's why I ran this analysis for a range of reasonable possibilities for what Dimorphos's density actually is. And so if it turns out that Didymos's density is lower, then that means that the actual value for the momentum enhancement factor might be a little bit lower, maybe closer to 2. And if Dimorphos were to turn out to be more dense than sort of the average expected value, then that might mean that the minimum enhancement factor was maybe closer to 5. But for now, the best fit that we have to the data available is 3.6. And these findings, plus a lot of other information about the mission and the experiment, were published in a special issue of the journal Nature, shown here on the left-hand side. And so I encourage anybody who's interested to go check that out. We have a nice set of 5 papers in here documenting the mission and the results, including the data that I just shared with you. This is a listing of the various U.S. institutions that were key in carrying out the DART mission, along with a few of our international partners, the Italian Space Agency, for example. And this is a complete list of all the different organizations who had personnel on our DART investigation team. And so this really highlights that planetary defense is an international issue and it requires international cooperation. And that's why we had a really strong international team. As I pointed out before, in October of 2024, ESA is launching a mission called Hera to go rendezvous with the Didymos system and do a really thorough characterization of it and tell us what the mass of each asteroid is, and along with a lot of other things. And in the meantime, we have a lot of outreach materials available on our DART website for anybody who's interested in checking that out. The links are here, and you're welcome to contact me afterwards if you don't get a chance to jot those down right now. And we also have 3D model files to print for the spacecraft and the binary asteroid system, even a toy bricks Lego-like model for building the spacecraft and other things. And that's the end of my prepared remarks. I'm happy to take any questions if there are any.
Thank you, Brent. This was an amazing talk about an amazing mission. Let's take a few questions, maybe a couple of questions. Any questions from the audience here or online? Any questions online? Please unmute yourself if you have a question online. If not, I have a question. We have a question on site, so maybe just come around and talk to the mic.
Thank you for the great presentation on an amazing mission. Very inspiring. The question I had was for the smart nav, the autonomous navigation, the guidance navigation control computer that actually targeted the asteroid on orbit. What was the sample rate required to do those fine adjustments for the onboard sensors?
I don't know the exact sample and calculation rate, but it was faster than a hertz. I can tell you that. The images that we saw in the telemetry were coming down at about a 1 hertz rate, but on board the spacecraft, it was processing the images and calculating the maneuvers faster than that, probably some tens of hertz. But I can let you know if you follow up with me.
Perfect. And then I guess on that as well, what kind of pointing accuracy requirements were needed to kind of hit that target from very large radius? Because obviously, as the farther away you are, your pointing accuracies determine how the fidelity of the thrust vectors, and then as you get closer and closer, you have much less time to correct for those pointing errors. So do you recall the pointing accuracy on that mission? I assume you used star trackers for the orbit determination. First, I added.
Yeah. Probably around the arc second level, but I don't have the exact number on hand. But I can get it and follow up with you on that.
Perfect. Thank you.
Thank you, Brent. The question that I was asked just about a week ago is: was there any effect on the main body's motion or the binary system motion as a result of that experiment?
Mm-hmm. Yes, there was. So the center of mass of the binary asteroid system was deflected by a very small amount. The measuring that is challenging though, because it's so small. But I think that there are some efforts underway to actually measure how much the center of mass of the system was deflected. And so I can check in with one of my colleagues who was working on that and see if they made any progress.
Fantastic. You have a question now?
Yeah, simple question. You know, you had this kind of a comet tail that was observed for quite a while afterwards. Did that also change the motion subsequently of the smaller of the two asteroids at Didymos?
Yeah.
So that act like a jet or a rocket exhaust, essentially, moving the body.
Right. A lot of that material was ejected fairly promptly, but it took a while to circulate out of the binary asteroid system and then get streamed away by the solar wind. So even though the tail grew and persisted for a while, that material had already carried its momentum away from the system shortly after the impact.
You have a question, Gary?
Yes. Gary Moyer here, technical chair. And my question, I don't know if you said what the difference in velocity was of the Demos, and to what degree did that change the orbital period? I'm sure you answered that already.
Yeah, the mass of the DART spacecraft, when it struck, was about 580 kilograms, and it hit at a relative velocity of about 6.1 kilometers per second. And the total change in the asteroid's velocity due to both the spacecraft's momentum and the ejecta momentum was about 2.7 millimeters per second, delta V on the asteroid.
Millimeters.
Small but meaningful amount. One
Yes.
more question, that, Brent, is that the predictions were different from the outcome in terms of the amount of deflection. What does it say about the importance of characterization of the object for planetary defense purposes?
Oh, it's very important because in order to design a reliable mission to deflect a hazardous asteroid away from the Earth, our models have to be well calibrated enough for us to be able to have a reasonable prediction that we have some confidence in for how much delta V or how much change in velocity will impart to the asteroid. And so missions like DART are absolutely essential to help us calibrate our computer models so that we have a better capability to predict what a given type of deflection mission will actually do to an asteroid in a real situation. So it's very, very important.
Thank you. One more question here? We have one more question from the audience here.
Thank you for a wonderful presentation, Brent. This is Madhu from USC. I saw one slide in which you showed a change in the orbit of the system, of the Dynamo system, rather than just the satellite. And also the tail of the, you've been watching the tail for some time. Any signs of water or anything in there that is unusual?
No. So first of all, the slide where it seemed like the whole binary asteroid system sort of up, that was just done in the animation to make the text labels easier to see. That wasn't meant to be representative of real physical motion. So that's what that was. The big observable change was just in the period of Dimorphos's orbit around Didymos. As I said before, the center of mass of the smaller amount, much more difficult to measure. And then as far as water, no, not really. The asteroids appear to be S-type, so more of a silicaceous composition. And there wasn't a lot of evidence of anything, of any volatiles like water, which would have, certainly added. So the volatilization or the vaporization of any volatiles would have added a lot of momentum to that ejecta plume. And there was a lot of spectroscopy done as part of those observations, but it pretty much confirmed what we had thought going into it, which was a sort of a stony S-type composition.
Thank you. Any question online? Yeah, there is a hand up by Ian. Can you speak up, Ian? Can you unmute yourself? Or is there something in the chat anybody can see?
Oh no, that was from an earlier presentation. That was the wrong. That's an old hand up.
All right. Okay. So last question from Gary.
This question is to Nahum. Yes. Have you at JPL or Aerospace modified your demonstration program based on this data?
Talking about DART? So I was not directly on the DART mission. That's something that Brent probably can answer. I'm sure it was a cross-organizational type of effort, international. So Brent, the question was, what sort of modifications were performed as part of your collaboration with JPL and other NASA centers?
So the DART team included scientists and engineers from a lot of different organizations. NASA Goddard Space Flight Center, where I work, there were a couple of us on the team. a lot of engineers and scientists at the Applied Physics Laboratory, also here in Maryland. Some of my colleagues from the University of Maryland as well were on the team, and then other universities around the country, and also other NASA centers and JPL. So, for example, the radar images that I showed you and the reduction of those data were all done by JPL scientists who operate the radar and do asteroid orbital dynamics. And then our navigation team for DART also included personnel from JPL working in conjunction with the APL personnel.
Okay, thank you so much, Brent. I'm looking forward for next DART.
Yeah, we're looking forward to the next DART, and then Nahum and I are also both chairs of the upcoming Planetary Defense Conference taking place next May of 2025 in South Africa, where we're going to bring together a lot of the same folks who worked on DART and other asteroid missions, and people who do other types of modeling. And so we're going to see a lot of other really interesting results, a lot of different efforts. Next May is participating. I'm sure Nahum can give you a lot more information.
Yeah, at the end, we'll do a sum up of the conference that's upcoming and other activities. But it's a pleasure collaborating with you, Brent. And I think now it's time to move to the next presentation by Nancy Wolfson. Thank you, Brent. Talk to you soon.
Yep, thanks. Bye-bye.
Hello.
Hi, everyone. Can you see me?
Yes, Nancy, we can see you. Fantastic.
Okay, fantastic. Yes. And so I'm sorry. Okay, for what it says. Okay. So sorry that I couldn't join you in person this time, but so it's going to be interesting going after Brent, after a fantastic technical presentation. We are more coming from the educational and policy perspective. So, and also discussing a little bit Asteroid Day and a few new initiatives that they have for Asteroid Day. Can everybody see the slides?
Yes.
Yes, okay. So this is between a work between Kevin and myself. And thank you everyone for putting this together. So we had one question coming from, again, the perspective of policy and education. What can we do to increase, enhance international cooperation? As right now, we have selected set of agencies involved in planetary defense, as everybody knows, ESA, NASA, JAXA, and a few other ones in some collaborating in the various activities that we have. However, we also agree that we're still fragmented in terms of international collaboration, and there are many nations that are not involved yet. The capacity that they could do something to act accordingly in case of an asteroid impact threat, or if they find us before we find them, an impact. So, Kevin, are you, who is running the slides? I would
I'm
like to know.
running the slides.
Oh, okay.
You're
I
on your
see.
first slide.
Okay, so that's the first one. Okay, so let's go ahead and, Kevin, why don't you introduce yourself briefly, and then I go with Asteroid Day.
Yeah, so my name is Kevin Berry. I have a master's in real estate development, and I got my way into space really looking at the question of how one would actually go about developing space. And I come at it from a more economics and finance perspective. And I have been doing a fair amount of work in the development of space solar power. And I have come to work with Nancy over the last couple of years. And she asked that I bring some of my ideas, which I presented on space debris and other topics, to discuss here at this conference. I was invited after a presentation. It's a mirror of the one that I gave at ISDC a couple of months ago here, or I guess 1 month ago. So with that, Nancy, I'll let you take and share with everybody about Asteroid Day.
Okay, fantastic. Yes, so we had an amazing conference. For the first time, we brought planetary defense to the International Space Development Conference run by the National Space Society. And we had a fantastic program, a technical session, a panel of experts for a student workshop. And also we were having a booth table to inform more about planetary defense. So I'm definitely looking forward for the 2025, and I will let you know in case if any of you wish to be involved in the International Space Development Conference by the National Space Society. I'm in charge of running the planetary defense activities there. So therefore, feel free to contact me at any time. Okay, let's go with Asteroid Day. So I'm not sure who is our audience today, but I'm going to be mindful, and I hope my experts are a little patient with us in this presentation, as probably I'm going to cover some basic information just in case. And of course, we're gonna go through the nitty gritty of the information so we can move forward through the 20-25 minutes that we have in front of us. So you already know who is Asteroid Day and what they do. But in case if you don't, you can read all the information that I will present in my slides, and that is going to be homework for most of you if this is the first time you're introduced to this topic. However, I will give you just a glimpse of what are we here for. So at the end, after a whole conversation in 2024 and Challenger in 2013, which was a meteor that Earthbust in Russia and damaged buildings and hurt people, I'm putting everything in very, very basic terms for all of us. Asteroid Day was sanctioned and approved by the United Nations. And in 2016, this happened at the General Assembly. And we declare, well, the United Nations declared June 30 as the International Asteroid Day. So it was created by various experts. Among those, we have Gregory Richards, Brian May. We also have Danica from the B12 Foundation, Stephen Hawkins, and Rusty, which is one of our astronauts from the Apollo, and so on and so forth. Now, the main idea behind Asteroid Day is to raise awareness that can be translated in various languages and can be taken around the world. This is why Asteroid Day is celebrated internationally. And what is amazing about Asteroid Day is that anyone can join and anyone can feel that they can participate as an action-oriented person and create their own event. Can you go to the next one, Kevin? Thank you. So my work at Asteroid Day is join them in Luxembourg every year. So every year the main event is run at the Luxembourg city. And I'm also part of the 100 plus signatures. And I'm dedicated to continue advertising and promoting Asteroid Day, because again, the educational initiatives that they have available for everyone. And as you can see, this was the presenters. Go back. It was the presenters at the Asteroid Day Luxembourg 2023. And you can see on the right side or left side with a black background, those are the presenters from the Luxembourg lecture 2013. And of course, probably you recognize many of those names, including Doreen, our dear astronaut and friend. And also we have on the one that is with the white background, some of the signatures that are very active in promoting Asteroid Day. We can go to the next one, please. Yes, and most of this is going to be homework. Okay, remember, this is what I talk about in the one that just passed in Luxembourg 2023, which is mainly raise awareness about not just getting involved the decision makers, but also there gotta be a way to get the local authorities or the local leaders of various communities also interested in planetary defense. And one of those could be the amateur astronomers and the citizen scientists. And that was the presentation from Luxembourg 2023. I also presented the reports from NASA and the International Federation of Red Cross, along with the FEMA reports to indicate that we all in agreement that we need to continue working toward getting new audiences involved in planetary defense. So that is a little quick rundown about my presentation from Luxembourg in 2023. We can go to the next one. And if you feel like I'm running through the slides, yes, a little bit, because we have a second presenter here. Okay, I'm almost at the end of this one. And so we're having two beautiful initiatives by Asteroid Day that if you're not familiar, this is the way that you can get involved in planetary defense. One of them has to do with the ransom mission. And if you're not familiar about the ransom mission, I really ask you to please get involved. And also you can sign the Asteroid Day letter in support of this ransom mission, which is basically related to the upcoming close encounter with the asteroid Apophis on April 13, 2029, which I'm excited about this because it presents an exceptional opportunity for all of us to really look into asteroid science, and also at the same time from those technical aspects switch into the public engagement. So during this close approach, it will be visible to over 2 billion people in the Western Europe and North Africa. So making this outstanding educational and public engagement opportunity. And of course, me coming from the educational and policy aspects, I'm very excited about this. Also, there are some concerns. But if you want to learn more about it, please take this as a homework and go to the asteroidday.org website and sign the letter that you see on your screen. On the other side, if you want to join an Asteroid Day, you can create your own presentations, navigate through the website, and you will have all sort of resources for teachers that can be used to create your own presentation and share this with not just your community, but your school, your university, your friends, your family. So no excuses to be a stranger. Asteroid Day give us the opportunity to actually become part of the community. And I welcome you to please support Asteroid Day and their new initiatives, either creating an event for your loved ones or joining the Ramses mission letter of support. And you can go to the next one, and I think that's the last one. And yeah, okay, back one. So this is the, you can go to the, yeah, this is the, oh yeah, this is just the photos, an amazing team of speakers at the Asteroid Day Luxembourg 2023. And you see myself somewhere, oh yeah, in the red dress. And also on the other side, you can see all the presenters for the lecture on the 28th and 29th of June, Luxembourg 2023. So these are just beautiful memories with people that I consider friends, and at the end, an extended family. Okay, Kevin, I'm gonna give you the floor. So go ahead with your section, and then I will complement with the last slides that I have. Sounds good?
Yep, sounds good.
Okay. Take it
so
away.
This is kind of picking up right where Nancy left off a little bit on Asteroid Day. I wanted to take a little bit of a pivot to talk about the Montreal Protocol and some of the lessons that we've learned and how humanity has dealt with historically large existential threats. in the past. The Montreal Protocol, if many of you are not familiar, it's the first universally ratified treaty, making it by and large perhaps the most successful international treaty of any kind. And the purpose of the treaty was primarily to deal with initially the spread of chlorofluorocarbons into the atmosphere, which caused significant damage to the ozone that is still present today. And through the work of this treaty over the past 30 years, it has already mitigated 2.5 degrees C of warming already, and it is going to continue to have that benefit. They expect the ozone will be almost entirely recovered by the mid-2060s based on the success of this treaty. Not only was it a well-signed treaty, it's been ratified 9 times, and it's been able to support and finance more than 8,600 projects all over the world to accelerate this transition as quickly as possible, even in areas where they may not have the capital means available to do it. This is largely supported by a large independent direct reporting from every country on their current status, science, engineering, and economics on how the problem might be fixed cheaper, better, or we might improve upon it, which has led to the many ratifications of it. Another figure which is important to this conversation is Elinor Ostrom. She was an economist who took and questioned Thomas Harding's almost stereotypical tragedy of the commons, that if you have a common area where everybody can have their sheep graze, that it makes sense for each individual sheep herd to add 1 more sheep, since it's a common grass and it'll be good. And if everyone makes that decision, eventually you end up with no grass. And this is a thought experiment which he stated very strongly, and Elinor Ostrom came in and said, that's not what happens in English pastures. You don't actually see the collapse of the ecology. People are able to work it out, even though the logic suggests they shouldn't be able to. And so she did several decades of work around the world looking at centuries of humanity successfully dealing with the commons, and has created through that work an observation of 8 separate principles on how we can successfully do that. These 8 principles, I probably don't have time to go over all of them. The long and short of it is you need to establish social cohesion, that a group wants to treat the commons as a privilege and not a right, that you have fair distribution of the costs and benefits to taking care of it. You have, again, fair and inclusive decision making with the authority to self-govern those decisions, monitoring those agreements, and having graduated sanctions for when people make an error, they have an ability to continue to come back into covenant in these systems, and they're not just immediately shunned from the system, but that repeated wrongdoing is eventually making it so you no longer have access to this privilege. And if there was more time, I could go in and discuss these further, but the crux of it is trying to establish that social glue that makes humans worry about the shadow of the future. That yes, it is in my personal best interest to do it in this way, but if all my neighbors look at me and they say, what are you doing? And they all remember that in every future engagement, it makes me sort of check myself and think about how does it affect the people around me. And that system of social pressure has proven to be extremely resilient and flexible to changing times and circumstance in many different climates, in many different ecosystems, from fisheries, forests, farming. It doesn't really matter. The principles hold up fairly well under scrutiny, and again, stably over centuries of time. We also have lots of examples, particularly in modern examples, where this doesn't work out. The Canadian fishery almost wiped itself out from overfishing because they said all fishing in the ocean is treated equally. If you ask any fisherman worth their salt, where's a good fishing spot, they don't point and say the ocean. And as a result, you have a very different dichotomy between these like gross generalizations. This is one of the issues that we see in space, is treating all space as if it is equal. The problems of having low Earth orbit, geoslot, having a near Earth object, space weather, those are not the same ecosystems. They don't play by the same rules. And to treat them as all space misses some of that critical nuance. And with that, I wanted to talk about this pyramid. And I'll talk about it as we continue on, but the long and short of it is we go identify the problem, create normative behaviors, develop mitigation practices to prevent it, and then remediation if all else fails. This is an expanding thing where you're going from information all the way up through wisdom. As your context and discovery level increases, you need to work your way up this pyramid. And if you don't have anything on those early steps, the whole thing comes crumbling down because you can't reach consensus on what a solution should be if you don't have an understanding of the problem you're trying to fix. So in planetary defense, that means a lot of different things to a lot of different people. I know that Nancy is going to talk to you further about Asteroid A and Earth objects in particular, but there are lots of different flavors, and each one of them is due a fair amount of study and investigation that we have not nearly enough time to discuss here today. To start off on this, establishing normative behaviors, you don't want to have any surprises. We want to have a planned response for things, acting responsibly from the beginning, and then we want to eventually start to build up towards, we know what the problem is, so how should we operate? Then the Montreal Protocol sort of shows how once you have that foundation of normative behaviors, then you can get mitigation practices. Different officials to kind of look over and make sure everybody's doing what they said they were going to do, having a solid economic and technical foundation for how to fix the problem. In the case of the Montreal Protocol, it's very true that the damage that was being caused was by human actors. So taking and reversing course was the normal thing. Planetary defense, nobody caused an asteroid, but it's still inevitable, and we still have to deal with it in a way that is economically and technically feasible and acceptable to all the people who are buying into that problem. And then eventually, if all else fails, and in the event damage has already been done, you have to pay for remediation of those efforts. And if you have a solid foundation of the other three pieces, remediation in the form that we have of asteroid defense is certainly something we can achieve. So with that, I'm going to kind of pass this back to Nancy, and we're going to talk about how this more specifically applies to planetary defense. Thanks. All right, Nancy, you have the floor.
Okay, thank you, Kevin. Fantastic. So let me see. Okay, so what is gonna, you can go back. So what is going to happen in the next slides is that we somehow are going to go over the very initial phase of what Kevin and I are looking to work on in the upcoming years. The Montreal Protocol is not an easy protocol to follow, as it has not just a lot of literature about it to be analyzed, but also there are some nuances and the many amendments that has been added to this protocol, which is also very flexible, therefore adding to its success as it was signed and then ratified by 197 countries, right? So very important protocol to look over and get some lessons from it as we continue moving into the future of planetary defense. And again, going from a fragmented international I don't know, a minimum international cooperation as we have it as right now, with very selected actors, to a more cohesive, comprehensive, and less fragmented international collaboration. So as Kevin was discussing these aspects early on his presentation, and you can read them, I'm gonna go to the next one, which applies a little bit more to planetary defense, right? And remember,
couple of minutes,
yes.
Nancy.
Okay, fantastic. Whew, a couple of minutes, and I thought I was running. Okay, so basically to discuss the Montreal Protocol in relation to planetary defense, it's important to understand the unique challenges and differences of each topic. So the primary differences lies in the nature of the threat they are addressing, right? The threat of the ozone and the ozone experts are primarily related to human activities affecting the ozone layer, while the threats addressed by planetary defense experts are cosmic in nature, involving objects such as asteroids that could collide with Earth and could disrupt human activities on Earth and potentially cause widespread spread, damage, and extinction at some level, right? So you can go to the next one. So the United Nations, navigated the cultural and demographic aspects to get the Montreal Protocol ratified by all countries through a combination of diplomacy, negotiation, and scientific evidence. These are elements that sooner or later will have to be applied when it comes to planetary defense and getting the various nations involved in planetary defense activities. And a few aspects that we need to look into it is obviously the joint observation and tracking programs, which already we have some collaboration going. Also the cooperative missions planning and execution. We also have some examples such as DART and coming up here. What is very unique about DART is abroad also coming from the business and private perspective. It included some PPP processes, which is public and private partnership, right? So we're not going to go in deep on this. You can go to the next one. Then also we want to look into, in relation to these 8 principles, we go to the next one. Yes, fantastic. So we already discussed the current ones that we kind of have some sort of cooperation that needs to be enhanced. Go to the next one. But information sharing and early warning systems still can be better and can be enhanced by what we can learn from the Montreal Protocol, as well as policy harmonization. Another way that we can learn and utilize the examples from the protocol is the resource allocation and funding initiatives that they had. Another one is capacity building and training programs. They also have a very strong system for conflict resolution mechanism on international levels. And the protocol success can be attributed to several factors, including the establishment of scientific consensus of the danger of the ozone depletion, right? The provision of financial assistance to the developing countries to help them organize and comply with the protocol, and the use, of course, of diplomatic pressure to encourage countries to ratify this agreement. These are long conversations that we are looking to have in the upcoming years as we continue exploring the Montreal Protocol. So conclusion, we can go to the last one. Yes, we already saw that one. Yeah, we can go to the last one. Yes, fantastic. So the Montreal Protocol involve multiple stakeholders, including government, industry, and environmental organizations. And this is something that is an active conversation within the planetary defense community, right? Because these help to build a broad coalition of support and to support planetary defense processes and to eventually have a widespread adoption of these processes and protocols that we seek to implement one day in the future when it comes to international collaboration. So let me see. And I'm just gonna mention a few things. I'm not gonna go through all of this. This is homework. So we go from tactics, norm, scaling, funding, and economics. We also going to be touching aspects as why an independent international panel of experts could establish to assess potential threats and provide recommendations for mitigating measures. Now, this panel could report directly to an international recognized authority, ensuring the decisions are based on credible, unbiased assessments, right? And last, in the context of planetary defense, so normative behavior translates into addressing and mitigating the consequences of any impact of disaster that do occur despite preventive efforts. This could involve post-impact recovery efforts such as debris removal, environmental remediation, and providing support to affected populations to minimize the long-term effects of planetary defense incidents. So at the end of the day, these examples only illustrate how government involvement and international agreements can be fostered to strengthen global collaboration in planetary defense, addressing the common goals, of course, of protecting Earth from potential cosmic hazards. And with this, we are at the end. Thank you.
Thank you, Nancy and Kevin. A very important aspect of the non-technical collaboration that is needed to solve the same problem. I think we will leave some questions, if there are any, to the end of today because we are a little bit behind schedule. We want to move forward with the agenda. Many, many thanks to both of you. And I think now we'll move directly to the next speaker, which is Arushi. Is you online now?
Thank you, everyone.
Thank you.
Thank
Yeah,
you.
appreciate your time, everyone.
Thank you. Let's see.
Hey, can you hear me?
Yes, yes, we can hear you, Arushi. Please introduce yourself with a couple of words. And I know that you've been already presenting at those events and other events. And so introduce yourself a little bit and go ahead with your talk.
For sure. Thank you so much. It's a pleasure to be here. I've been listening to so many interesting presentations so far. So my name is Arushi, and I'm a grade 9 student from Toronto, Canada. And for the past few years, I have been working on planetary defense, on detecting asteroids. So I'm going to be sharing a bit about my research in the past few years. So let me just open up my slides. Here we go. So today I'll be talking to you guys about how I merged serendipitous asteroid observations from sky surveys with dense observations from telescopes from citizen scientists to accurately determine the physical properties of asteroids. So just a quick introduction. I'm sure all of you are aware, there's about 1.3 million known asteroids in our solar system so far, and hundreds of near asteroids continue to be discovered every month. If one of these asteroids were on collision course with the Earth, we would need to know their physical properties like size, strength, and composition to be able to deflect it. But unfortunately, more asteroids are being discovered than we're able to analyze. And the reason for this is because analysis of asteroids require observations across a long period of time, from 3 to 5 years, with changing phase angle of the asteroid. And we do not have enough telescope time to get these observations. So my project had 3 main goals. First, develop algorithms that can accelerate the characterization of asteroids by merging serendipitous asteroids observations from sky surveys. So these could be surveys that are just observing the skies for supernovas, for stars, whatever. And by capturing these serendipitous observations from the archives of the sky surveys, I would be able to obtain these 3 to 5 years of observations needed. And then, by combining them with dense observations from citizen scientists, I would be able to complement that data. Second goal, I'm sure you guys have all heard about NASA's DART mission with the previous presentations, but my goal was also to be able to use my algorithm to measure the physical properties of the Didymos asteroid system before, during, and after NASA's DART mission and measure the change in physical properties. And finally, I wanted to use my algorithm and expand it to thousands of asteroids to characterize these large asteroid populations and be able to find information about the compositional diversity of our solar system. So how did I go about this? So as I mentioned before, I used sky surveys to capture observations across a long period of time. In particular, I focused on 2 sky surveys, the Gaia Space Survey, as well as the Zuki Transient Facility Ground Survey. Then, I complemented it with data from several Barbee telescopes across the globe. And using these combined observations, I would be able to get all the observations I would need. So here's just a quick rundown of all of the observations and telescopes I used. Some of the primary observations. So all 3 Barbee telescopes were spread across the globe in places like Canada, Australia, Chile, and Spain. And there was about 5 to 6 Barbee telescopes in all. And then I also used open data sets like the Asteroid Light Curve Database, or ALCDEF, where citizen scientists had shared their observations of asteroids. So I created an algorithm in Python which followed a 6-step methodology for finding physical properties. First, using my images, I found all known stars and asteroids using open data sets. So the Gaia early data release, sorry, 3 star catalog to find all known stars in my image, and the Horizons database from NASA to find all known asteroids. Then I used weighted mean to center all of these asteroids in my image. Second, now that I had the asteroid Didymos in this case in the picture, I wanted to find its brightness. To do so, I created apertures of varying sizes. I created an inner aperture to measure the pixel brightness of the asteroid itself. And I created an outer analyst around it to measure background noise. Subtracting the two, I was able to find the total pixel brightness of the asteroid. To find the correct aperture size to use, I used slope analysis and median. Finding the right aperture size was very important, because if it were too small, it wouldn't contain the full brightness of the asteroid, and if it were too big, it would contain too much background noise. Third, this wasn't enough, because since my observations could be spread across different years, observing conditions, air mass, and everything would change. So to account for these, I used comparison stars. These are stars with known and constant brightness. So by measuring their change in instrument magnitude caused by weather conditions, I could apply these to the asteroid's instrument magnitude to find its computed magnitude. Fourth, there was one more offset to apply. Because asteroids are always orbiting around the sun, which means their distance from the sun and Earth is always changing, causing changes to its brightness. To account for these, I applied offsets that benchmark the asteroid brightness to 1 astronomical unit from the Earth and the sun, giving the reduced magnitude. So now here's where the interesting part comes along. So this is where I would take observations at different phase angles using the sky surveys. And once I was able to plot it, as you can see in the right graph, observations from 0 to 7 degrees, you will notice a very steep surge. And this is caused by the opposition effect. Whereas, after around 7 degrees in phase angle, you will see that the graph becomes more linear as this huge surge disappears. So, by extending the phase curve to 0 phase angle, I was able to find the absolute magnitude of the asteroid. And I was also able to find the slope parameter g. Sixth, using my dense observations, I was able to find the rotation and mutual orbital period of the asteroid. Because since asteroids are very small, they do not have enough gravity to hold them together. So as they rotate, different sides reflect light differently as they are irregular in shape, causing 2 maximas and 2 minimas in their light curve. If the asteroid was a binary asteroid, such as with Didymos, I could subtract the rotation period from the primary light curve and repeat a similar process to finding the mutual orbital period. So I applied this algorithm to Didymos and got 4 results. First, I was able to create a phase curve by fitting observations from the ZTF telescope as well as ALGLEF. I found the absolute magnitude of Didymos to be 18.14 and its slope parameter g to be 0.16. Second, I was able to find the geometric albedo of the asteroid, and using the geometric albedo and the absolute magnitude, I was able to find the size of Didymos to be 840 meters. Third, by fitting my dense light curves to different rotation periods, and by calculating the root mean square error, I was able to use congruent modulo to find the best fit. I found the rotation period of Didymos to be 2.26 hours, and it did not change after the dart impact. After subtracting the rotation period, I followed a similar process to find the mutual orbital period. I found it to be 11 hours and 55 minutes, and actually reduced by 35 minutes post-impact. So what does this 35-minute decrease mean? So, using Kepler's third law, a 35-minute decrease in the mutual orbital period translates to a 40-meter reduction in its orbital radius, proving successful deflection. Using the rotation period and the size of the asteroid, I was also able to determine its strength and found Didymos to be rubble-based. Third, I applied this algorithm to 2,100 different asteroids, including targets of space missions, binary asteroids, and understudied asteroids, and I was able to determine all of their physical properties by combining sparse and dense photometry. Fourth, using the geometric albedo of asteroids, I can also determine their composition, since asteroids are mostly not internally differentiated. Knowing the albedo of Didymos, I found it to be of silicaneous or metallic type. Then, by expanding it to 2,100 asteroids, I plotted their asteroid type over semi-major axis. I found that 58% of asteroids were carbonaceous, rising to over 70% in the outer main belt, suggesting cool, volatile-rich conditions during solar system formation. Errors and limitations. All my observations had a signal-to-noise ratio of about 100, which meant the measurement uncertainty was 0.01. In conclusion, I was able to succeed at all my goals. I was able to create algorithms that accelerate asteroid characterization, apply them to the Didymos system, and then apply them to 2100 asteroids. So a bit of outreach, I was able to present some of my preliminary results to NASA's DART team at the 2023 Planetary Defense Conference, where I got to talk to several members of NASA's DART team, which was an amazing experience. In addition, I published 2 peer-reviewed papers about my algorithms as well as Didymos. So thank you so much. I'd be happy to answer any questions.
First of all, congratulations. This is an amazing piece of work, in my opinion, and it's made progress since the last couple of presentations that you made. So I predict a bright future for you as a scientist in the planetary defense area. And so now let's see if there are any questions from the audience.
Right?
Hmm? Yes, yes. You deserve applause from the audience here. Any questions? You do? Okay, a question from here. Madhu, please talk to the mic.
I mean, I second what Nahum said, but what is the equipment you're using, Arushi?
Sorry, could you repeat that question?
What is the equipment that you're using to get all this data? Because much of it seems to be direct data from the skies.
Yeah, that's a great question. So for my images, I used a mix of data from Barbee telescopes. So I wrote research proposals to a few Barbee telescopes located across the globe, where I was able to take my own primary observations. And for the rest, I used open data sets like ALDEF, which already gave the light curves of the asteroid. And in addition, I used sky surveys to obtain all of my longer period observations. So there they gave data in a mixed format. Some sky surveys gave the images and I was able to process them myself. And some of these sky surveys gave the light curves.
Nahum, I was asking also about the primary equipment. Can you ask her about the telescope?
Yes, so the question is about the primary equipment that you use, the telescopes and such.
That's a great question. Yeah, so for the telescopes, they were located all across the world. One example is, for example, the Burgafni Observatory. So all of these were remote telescopes. They were about 0.4 or 0.5 meters in diameter. Normally, I just used like Johnson's red filter to keep it standard across all observations. And so all of the equipments were slightly different. So I customized my algorithm to basically work on any of the equipments.
Yes, very professional. That's a comment that comes from here. Any other questions or comments from the audience here or online? So Arushi, what is your next goal? What is your next objective in the next, let's say, year or two?
That's a great question. I actually have not decided yet. Definitely asteroids is a very exciting topic. There are several missions that are coming ahead from JAXA, different space agencies all across the world. And one of my future goals is definitely to help and provide citizen science observations and whatever research I can do to support these missions. So that's definitely one goal I'm sure of. For the rest, I'll have to see.
Are you a member of AIAA?
Are you a member of AIAA?
Yes, I am.
Oh, great. The American or the Canadian? Maybe both. I remember a couple of years ago, you were involved with some observations of asteroid Apophis.
Yeah, that is true. And I got to present my results at the 2021 Planetary Defense Conference, which was really cool. That was virtual. But yeah, since Apophis was having a close by, I thought, why not do some fun science? So I took a few observations of Apophis from remote telescopes, and I was able to determine how fast it was moving.
Fantastic. What are your plans for 2029?
That's a great question. Definitely, I'm really excited for that. The Prof is supposed to come very close, and I'm waiting for the magnitude to drop now so I can take a few more observations and see what I can do with them.
Great. We are looking forward to more interesting presentations by you in the future. Thank you so much.
Thank you so much for having me.
Thank you. And I think our next speaker is Madhu, right?
Oh, yeah, okay, good. Shall I just stop from here, or it's okay?
Yes, yes.
You can. Because your slide, my slides are on this machine here.
Yes, yes. So Madhu, please introduce yourself, and the floor is yours.
Thank you. Let's go on the slides, and let me see how well I did at 4 a.m. in the morning. My name is Madhu Thangavelu, and I think I know some of you here, but if I don't, I see Bradley over there, and I see Mark. So anyhow, I wanted to highlight a few things that some of you may not know, and some of you may. How many of you know these folks? I was just curious. What is you see? You see? This is the long history, the arc of history of planetary defense. On the left is Alan Harris, who worked on the power law. And on the right, you see David Morrison, who was known as Dr. Doom. He spent a lot of time telling people around the world how bad things can get, right?
I'm not sure that they're seeing the right slide at the moment.
Yeah. Oh, okay. Well, everybody cannot see it. Huh? All right. Ken is going to work this through.
They can hear you, but not see what you want.
What are you saying? Okay.
So,
okay.
I think it's coming up. Not yet.
Any better? Remote group, can you see the image or no?
Okay, now I can see it.
Oh,
so
okay.
Yeah.
Okay, so I was just mentioning, asking folks, how many of you knew these people? And on the left is Alan Harris, and on the right is David Morrison. And these are some of the folks who've been making noise about how dangerous things can get with the general activities in the solar system if we don't pay attention. And let's move on. Do I get a clicker or how do we do this? Let me go this way. Yeah. Whoops, not moving. So let me walk you through. You know, it's wonderful to hear all the history that went on in the past from the various speakers. And every time I watch these things now, I learn a lot myself, and it's very enjoyable. So the history of what happened at USC. I happen to have a foot in the School of Engineering within the Department of Astronautical Engineering, and also in the School of Architecture. My background is in those two disciplines. You may all know that Neil Armstrong passed through our gates of our school to get his degree, and he was assigned the Apollo mission commandership when he was in school, and that is his thesis. So we have this much bigger than life sculpture of Neil Armstrong, and sometimes students come. My classes happen to be in the evening, and you see a group from UCL, University College London, who came to our school, and they're posting the picture. All of you need to know that USC has an astronautical engineering program as opposed to an aerospace engineering program, and we are a selective group, and we are looking at things, particularly the spacecraft. And my class, which Nahum loves to come to, is based on very simple premise. please give us your idea. We'll take care of whether it works or not later on. But the most important thing in this class is to give your idea up, show a visual, and speak to it for not more than even 5 or 10 minutes, right now? But anyhow, we do this, and because we are academia, we can't care less about what industry or NASA thinks. We are here to bring our ideas out, and I can see Mark already smiling. He's another reviewer in the class, and Bradley has taught in the class, right? So we are in good company here, folks. Good mafia. So our friends include all of these people. Some here in the audience, and Buzz Aldrin comes in incognito because otherwise he charges a huge honorarium, and he loves our class. In the spring, I teach in the School of Architecture, where they throw arrows at me for being a space nut, not knowing anything about how the world lives. And so I try to tackle them by saying, hey, listen, you can get hit by comets. You can get hit by asteroids if they're not careful. And so they tend to listen to me some other time. And as you see, it's a worldly mission. You have people from Paris, you have people from here, from Canada, from Turkey, India, Iran, and China. They all come to school. It makes them global effort. Now, one thing we all like to talk about and be clear about is that much of the space community is about a fraction of humanity. And while architects and engineers of other disciplines spend most of their time looking downwards and looking at real problems, we go outside and look for comets and what things can do. And how do we connect all this? Through the United Nations Sustainable Development Goals. Every one of those tiles have something involved with space. As you know, just a few days ago, Russia busted up one of their old satellites. Debris is a problem, folks, and I think the United Nations is going to get on this very soon. And planet Earth, too, is suffering because of our activities. Much of it we do knowingly and for our benefit. But unfortunately, some of it is hurting Mother Earth. We want to look at Ostrom's work from Sweden to tell you what is going on with planet Earth, particularly land surfaces and the atmosphere and the oceans. And my answer to all of this, as always, is innovation. The thing that makes us different from the rest of nature's magnificent creatures is our idea to create and go over the difficulties we are posed with. Much of it is written in our books, and I'm glad to report to you we are haggling the 3rd edition, Nahum, and we are hoping to see something come out of it by Christmas. We'll see. Buzz Aldrin wrote the foreword, and he always says, Madhu, it's important that we discuss and debate in the early stages because that is when ideas are important. And then once we get to a good idea, we can collaborate with the world, with the rest of the world. Now, who got me into planetary difference is very interesting. One day, this person on the right, Professor Wickman from Claremont McKenna, comes into class and says, Madhu, did you attend the Long Beach conference on planetary difference? And I go, no. Then I called my neighbor, Bill Ayler, and I said, yes, we missed you, but this was a very interesting meeting. No, we were there, right? Oh, this was a little bit early. I think it was 2004 or something, around that period, early 2000s. Anyhow, you're coming to our class. I would like you all to look at the archives to see what we did in 2013. We call it Eden Shield, Concepts and Strategies for Planetary Difference. And what came up very early on is that the studies being done then and also now seem to be worried about things happening in the years to decades to centuries. We call them long-term mitigation and deflection and strategies. But what are we doing about short-term mitigation? And when things can happen very quickly, months to weeks to days. And so we worried about this, and comets came to mind, particularly the ones from the Oort cloud, which come in extremely high inclination and very energetic, given the distances they travel. And here's a nice one from Bill that said I wonder how he is doing, Nahum, but Bill has retired from Aerospace Corp and did some incredible work while he was there, assigning an entire department to orbital debris and what he called re-entry missions, right? Yes. Seeing how things explode. And anyhow, here you see, what I would like you to see is that it takes extremely high energies if you're very close to days of impact. And if you can drag this out to days and months and years, we think we have a better handle. But this is not quite true, because if you look at the skies, we are getting hit by things, as some of the earlier slides from others mentioned. I think you know the differences between asteroids and comets by now. Whenever I see equations, little equations, I look at the exponent. And that is when I start to worry. Whenever you go to squares, cubes, and the fourth order and so on, you really have to pay attention to that variable. So this is our project from the 2013 slides. I want all of you to take a look at it. It's on our archives. One of the ideas that came up then was one of the commanders from U.S. Air Force Command was with us, and he said we should take little bits of asteroids in the asteroid belt, and particularly around the Jovian systems. We have the Trojans and the Greeks and so on, and fit them up with the little devices and fly them out and take them out as they come. And I'm so happy to say that Nahum presented some very interesting things about comets at the ISDC. And so this requires preparation. So no go. Then B, a very, very excited young woman came to class and said, if we are going to be doing solar power satellites, we can turn those beams around and hit approaching comets and asteroids with them. And some studies that you're going to probably hear soon from our friend in UC Santa Barbara will tell you how we can do this. So here you see B's depiction of a solar power satellites turned around shooting at an incoming comet. And this is the part that we all miss, which I was hoping that Leviticus Lewis would talk to us. He was in the news the other day, and it says, currently, we don't have anything for asteroids or comets or anything that can help us. And that's why the earlier administrator mentioned, God forbid, we got to pray and pray very hard. So we looked at what we could do once an asteroid impacts. And I think Jay Melosh and others have spent a lot of time talking about it. Go underground. You know what? It's happening in Ukraine now. It's happening in war-torn regions now. But what do people do when they get bombed? They go underground. And you have to think about this. And so those kind of studies happened. And we are not new thinking about these things. Buckminster Fuller, a well-known architect from many years ago, suggested covering New York with a dome so that you can keep the smog out. And of course, when things go from bad to worse, doctors come in, and this was another thing that was talked about in the class. And the idea of isolated, confined environments is not new, particularly for the space profession, human spaceflight people. There was a doctor in the class, a very well-known doctor. Did you meet him, Nahum, or did you see Dr. Stubby? Probably not. Eagle Scout person who has done a lot of things. He went on to say, there's a lot of publications in JAMA and others that talk about what to do when natural disasters occur. And Dr. Stubby used to be passed on. He would say that the gold standard for studying stress is heart rate variability. we knew this from the Russians before we started using it for our restaurants, you know, and it's important. So now, moving on, after the class, somebody got wind, and I think Nahum was probably at this meeting when we talked about Q-bolt, which came out of one study from our, this is about Q, as you know, is the quality factor in resonance. And if you apply resonance in the exact manner you need, you can do magical things like break down buildings, shatter glass, and so on. And we can do this if we can, bombard approaching lights. And as you know, you may not know, or maybe you do. Maybe Gary knows there. When STS went up, they did some tests before, and quickly found out there was some harmonic problems with the SSME. And if they hadn't done it, they would have blown it up on the pad. So quickly, acoustics engineers became very, very important. And so these are important things to know. And then nowadays, we know that we can use, we can combine beams, and using smaller apertures, we can combine them together to form very powerful beams. Thin disk laser technology is coming, and I think, if I remember right, 1 kilogram per kilowatt has been passed. So now soldiers can carry laser weapons, and this is getting to be scary. And I wrote an article for Space News, and I went in there to pull it up, and it's been taken out, so I don't know what the story is on that. But anyway, so line of sight, speed of light is the thing to think about, folks. I call it lost salt, and we'll have some more papers coming out soon on that. Look at something, take it out. And this means it's very short-term engagement and consequences. So ISU got wind of this, the International Space University, that's running right now in Houston at Rice University. And they got wind of this work and said, Madhu, we want you to chair a program. So yours truly go there. I had no idea what I was getting into, Nahum. I really did not. There were 40 young people from all over the world, many of them in their own military camps and so on, coming in and listening to how we would bust comets and asteroids. You may all know this. In case you haven't seen a slide in our presentation today, you need to know that planetary defense is considered the #1 choice from the public. We can't care less what the scientists think. We can't care even less what NASA thinks. But this is a few research that tells you. Most of the people on the planet think planetary defense is more important than anything else. And then going to our paper that came out of ISU, I recently found out that it is the most read report from all of ISU's reports. And then Nahum got interested with one of our students, Nicola. Nicola wrote a book. And so once in a while we get very interesting. And the guy behind him is from South Korea. He's a military man. So what did ISU do? ISU is a very social group of people who get together and really try to tie loose ends and massage each other and say this is a global affair. And we talked about how we could get the whole world together. And here you see even the dinosaur came to our presentation. And then I had asked Bill to come and talk, and Bill says, no, the right man you need is Nahum. That is how I met Nahum for the first time. Of course, ISU is a place where we do socializing, and here you see the party. And Phil Lubin was there, Jeff Landis was there, and it was a very interesting program. And here you see Nahum again. And you see Kathy Plesko. Nahum, we had a good time walking around with her, remember? That's right. And they're all engaged in some form of astronautical engineering. We went on further to produce some papers in the Lunar Sentinel. We said it's not only the Earth, folks, we start worrying about the moon too, because we are a system, Earth-Moon system. Then we studied some what we could do with the high energy lasers. But all of you know this is the case, and we know that it could also be used to detect stuff on the lunar surface. How are we doing on time now? Very good. And so we thought about, it's time to go? All right, good, there we go. So planetary defense, as we know now, is really about observation and detection. Nothing much is happening since Zambrano works, in the early 2000s. I'm more worried about cometary fragments and comets, and so we'll be looking at that in a little more detail. We are not prepared. We got to do something about it, folks. And maybe the moon is an area where we can place something, and we have to study what the threat level gates are like, and place some interesting little prototypes there. I think we heard Brent talk, Brent Barbee. This is a difficult thing to worry about. I'm still looking at low sol as the only possible way to engage very quickly. And folks, just a few days ago, Leviticus Lewis presented this exercise. Again, aftermath is as important as mitigation. And I wish Dawood was here to talk about asteroids. We all know about this. And comets are all over the world. Comets are all over the world, and all over the solar system and extrasolar system. We have to worry about that. And this was a pun intended movie. I don't know how many of you watched it. I thought it was terribly boring. Planetary defense is real. I'm going to give you a list of references that I enjoy collecting them, and it's chronological, and I'll leave that with Ken. I hope all of you leave your presentations. Thank you. Now, folks, Asteroid Day is coming up tomorrow. Yes, please. I would like to share slides, and maybe the rest of it, because there are some beautiful slides from the presenters.
So Madhu, I just received breaking news
Okay.
that an asteroid is going to hit your infrastructure on the moon tomorrow. What are you going to do?
Absolutely. Pray. Pray in your own language, guys. In your own religion. It happens to a multiplicity.
One question for Madhu, if any.
Oh, it's all so clear, isn't it?
Okay. That was the speed of light, I think, this presentation. Thank you, Madhu. Always fascinating.
Thank you.
You have a question? Okay,
Sorry, I just have a quick one. So like you mentioned that in your course, you can present like ideas.
Absolutely.
Can
the only thing you do in the course, if you don't have an idea, don't come to class.
So can anybody from outside also do that, or is it just USC students?
No, anybody who will pay USC tuition can come and see.
So very
Mark will tell you that.
Okay, one question from Gary.
Oh, Gary.
Sure. Having worked on a few space-based laser and several others, do you have any idea what the existing power level would do to an object?
What I heard from there are several people working high energy lasers, and all of them are in the black room, because as you know, high energy lasers can do very dangerous things. If you go into the industry, take a look at it, you'll see extremely high power lasers cutting through each per second. But our difficulties are Gaussian. As you go further out, things get difficult.
Sasha.
But I think I can't tell I can't tell you more than I know. Claude Phipps. Take a look at the works of Claude Phipps. Have you met him, Claude Phipps? the guy who does high energy laser conferences?
Maybe.
Yeah, sure.
Yeah, I'm sure I have. I'm sure I have.
They are looking at extremely high power of very low mass. And thin disk lasers are one of them, but there are other magical things that they won't talk to us.
Thank you, Madhu, and everybody else. And I think now we will move forward to the next speaker, which is Sasha from Santa Barbara University, I believe, right?
Yes.
That's correct. Yes. Can you hear me?
And they are the students of.
They are the students of Professor Lubin from Santa Barbara. And I think you're going to talk about very interesting new concept that you are doing some research on now. So take it away, Sasha.
That's right. Can you hear me?
Very well.
Oh, we can hear you.
Great. Alrighty. Yes. So my name is Alexander Cohen, although I go by Sasha. I'm a researcher in Dr. Philip Lubin's group in the physics department at UC Santa Barbara. And I'll be presenting the results of an ongoing supercomputer simulation campaign that's studying the feasibility of a planetary defense technique that we like to internally call PI, or pulverize it. We do have a history in our group in planetary defense, as was mentioned before, in the directed energy area, but this is a novel method that's actually independent from that work, which we'll be presenting here today. And I'll be presenting in tandem with my colleague, Brent Bailey, who will be presenting the ground effects portion of this work in the talk after mine. Okay. All right, so PI, how does it work? So PI works by making use of hypervelocity impacts with specially designed high density, high aspect ratio tungsten cylinders. The primary distinction between PI and, say, classical deflection is that we focus on utilizing the transfer of the kinetic energy of the impactor to the target rather than the momentum to the target. And this enables a wide variety of use cases and a multimodal mode of operation, which allows for mitigation of asteroids both in a terminal mode with very short warning times, as Brin will be discussing later, and also in long warning time modes that are more analogous to classical deflection. So in general, we consider hypervelocity impacts, so impacts with velocity greater than 10 kilometers per second. And in that regime, the impactor vaporizes itself and the target material on a timescale in the first few hundred microseconds, which forms a high pressure plasma cloud local to the impact site, which on a longer time scale expands and kind of acts like a gas expansion engine, which acts to disrupt the target. In disruptive modes of operation, the entire target is reduced into a distribution of fragments, which are then allowed to enter the atmosphere and are mitigated by burning up at high altitudes in the atmosphere, which again is the subject of Brent Bailey's talk next. But this can also operate in enhanced deflection mode, where, as was discussed by Brent Barbee before, you can achieve an extremely high momentum enhancement factor by ejecting a significant amount of material off the surface of the asteroid. And I'll show simulations of that in a bit. So how do we actually study this thing? We study this using the Lawrence Livermore code AL3D, which is a multi-physics hydrocode, which uses extreme equations of state to study materials in extreme shocked states. So we use tabular equations of state, which are numerical models that describe the thermodynamic behavior of materials to describe our asteroid materials. For the simulations shown here, we focus specifically on weakly bound rubble pile asteroids, although it's our goal in the future to expand our simulations out to a wider variety of asteroids, including high density, more homogeneous asteroids. But again, like I said, the simulations I'm presenting here today focus on loosely bound rubble pile asteroids, similar to the ones I show here on the plot. So this is an example of a 500-meter spherical asteroid with a boulder distribution on the inside. For our simulations, we distribute the strength throughout the boulders from boulder to boulder, as well as within each boulder, which is shown here on the right. We use Weibull distributions, which are a common method to describe the variations in strengths in natural rocky materials. And this allows us to simulate fracture dynamics in hypervelocity impacts. So you can see that the variety of strengths in our boulders is actually, the disparity in strengths is quite high. The weakest of our boulders are similar to hardened soil in their strengths, And our strongest boulders are similar to high-strength steel and titanium in their strengths, which is an extremely conservative material strength model, but it's useful to put an upper bound on our strengths. And this is a realization of this strength distribution in an actual three-dimensional model. And you can see here in cross-section, you can see how the strength varies within these various ranges. This green boulder, for example, corresponds to this 50 to 100 megapascal strength range, while these blue boulders correspond to the much higher strength. I should also note that we simulate a very weak binder material, which permeates the space between the boulders to simulate the very weak cohesive binding expected in rubble pile asteroids. We run these simulations using the NASA high-end computing capability. The NASA at NASA Ames, the supercomputing facility there offers multiple independent supercomputers with varying system architectures. Here on the left, I show the Pleiades supercomputer, and on the right here is the Aitken supercomputer. A typical simulation of ours runs on 16 Aitken nodes. Each Aitken node has two 64-core CPU processors per node. So at 16 nodes, we run on a little over 2,000 CPU cores per simulation. So the calculations are rather large, and we're producing multi-terabyte data sets with each calculation. So in the next series of slides, I'm going to present a series of simulation results progressing from smaller targets all the way to larger targets. So here I'll show a simulation of a 20-meter rubble pile asteroid. You'll notice that all the simulations I'm presenting here and in our early work, the containers for our boulder distributions are all spherical, which means our targets are all spherical. And part of our goal in future work is to use actual asteroid shape models to improve the validity of these results. But for now, we're just focusing on spherical asteroids. You can see here in the two equatorial two-dimensional cross sections, I show the boulder material strengths again. And the blue color scale corresponds to material density in grams per cubic centimeter. This magenta cylinder here is the penetrator. In this case, it's a 100 kilogram tungsten cylinder with a 10:1 aspect ratio. And I'll go ahead and let this play out. You can see how in the first few hundred microseconds, the penetrator has been completely vaporized and converted into a high temperature material. And then this high temperature, high density asteroid material is ejected in a rather collimated way outside the entrance cavity, which actually induces a significant amount of thrust for a transient period of time. It's actually comparable to the thrust of a heavy lift vehicle such as a Saturn V for about 1 second. And then over the course of the next few thousand microseconds, you can see how the material deforms plastically due to being failed after the shock propagates through the asteroid, and you'll see some plots of the shock propagation later on in my presentation. But this is an example of what we call an early time simulation, where we use a mesh resolution that resolves the radius of the penetrator very finely, so we resolve the impact site very finely. But this is a computationally intensive resolution to continue the simulation with to macroscopic timescales. So as you'll see in a little while, we couple two simulations together, this one with an early high resolution mesh to another simulation with a low resolution mesh and a much larger region to extend it out to much longer timescales. So moving on here, I'll show the same simulation just with the material velocity shown. The base units of the simulation are a little strange in centimeters per microsecond, so I've included the speeds in kilometers per second and meters per second here for each tick on the color scale. And I've also shown vectors to show the material direction. You can see following the material velocity vectors how the material being ejected out of the entrance cavity is very collimated and how this contributes to the momentum enhancement factor. You can see that happening right now, and you can see how the material being ejected is coming out at about 1 kilometer per second, this low density material. So moving on, we will increase in target size now. So this is the exact same 100 kilogram tungsten penetrator incident on a 50-meter target rather than a 20-meter target. And you'll notice that before I let this simulation continue on, this is an example of a late time simulation where the actual impact has already occurred and was resolved with a very high spatial resolution. And we've coupled to a lower spatial resolution simulation to extend this out to a larger region and a longer time. So we're resolving this simulation to about a cubic meter spatial resolution. You can see how after the impact occurs, the impact site rapidly expands radially, and a significant amount of material is dissociated from the original object in the form of fragments with a certain size distribution, and I'll talk about that in a bit. But we can absolutely say we've achieved what we'd like to call robust disruption of this type of target with a measly 100 kilogram penetrator impacting at 20 kilometers per second. So moving on, we can study the fragment statistics of this case. So on the left, I show histograms of the fragment masses in black, the fragment speeds in red, and the fragment diameters in blue. I've also shown in this vertical dashed line the gravitational escape speed of the original object, which is about 2.1 centimeters per second. And you can see here, based on the location of the fragment speed distribution, how all the fragment speeds lie at least an order of magnitude, if not more, above the gravitational escape speed. So none of these fragments will gravitationally recombine on a much longer timescale. The average fragment speed at this time is about 17 meters per second. And the average fragment size is about 1/2 of a meter, whereas the maximum size obviously is this persistent fragment. But as I'll discuss later, and you'll see in plots of the damage, when we have robust disruption of this type, when we have a persistent fragment of this nature that persists at these longer timescales, when you study the internal damage of the material here, and you look at the distribution of velocity, you can see how there's no more cohesive strength left in this material, and it's all moving outwards radially at speeds many times greater than the gravitational escape speed. So we can be fairly confident that this thing will come apart into fragments of a similar size distribution as shown here in the blue fragment size distribution. Now, these results suggest that a 100 kilogram penetrator is sufficient to completely mitigate such an object. And similarly, if you were to exhaust the payload capacity of, for example, a Falcon 9 with 25 100 kilogram penetrators, you could be fairly confident that you've achieved what we like to call a single launcher solution for threats in the 20 to about a 150 meter diameter range, where with a single launcher type, such as a Falcon 9, and a standardized payload, you could effectively mitigate threats within this range in this disruptive mitigation mode. Another thing to note is this specific impact energy, which we define as the ratio of the kinetic energy of the impactor to the mass of the target. And it's an estimate of, if you were to assume that all of this kinetic energy of the impactor were to be perfectly coupled into every unit of mass of the target, this would be the amount of energy per unit mass that the fragments have as a result. There was a study done by Martin Jutsi studying the catastrophic limit of the limit of catastrophic disruption for sphere-on-sphere type impacts, and their specific impact energy threshold above which they achieve catastrophic disruption is about 100 joules per kilogram, and we use that as kind of a baseline to determine whether or not we expect that a certain hypervelocity impact scenario will achieve robust disruption. And you can see how in this case we're well above 2 times that limit, and we do indeed achieve robust disruption. So another interesting question to answer is whether distributing the penetrator mass across multiple impactors is more efficient than concentrating the penetrator mass in a single impactor. So this is an example of 5 100 kilogram impactors in a plus configuration, 1 in the center and 1 in each quadrant. And I'll show the results of this simulation in comparison with the same penetrator mass concentrated into a single penetrator. So I'll move on here and we can discuss the fragment statistics of this simulation. You can see again how we've plotted the gravitational escape speed as a vertical line here. It's about 3.4 centimeters per second for the original object. And the fragment speed distribution shown here in green again lies at least about an order of magnitude above that. So this thing will not, at least for the fragments, will not gravitationally recombine. And in this case, I've also plotted in red the original boulder size distribution, so you can compare the size of the fragments to the original size of the boulders. One question we've been asked is whether we're actually dissociating the boulders inside the asteroid or whether we're actually just ejecting them. And this answers the question pretty pretty completely in that we are just disrupting the asteroid to size scales below the initial boulder size distribution. And then here in this inset plot, I show the material damage at 2 different times. You can see here how within about 0.2 of a second after the shockwave has propagated through the asteroid, we've achieved pretty much complete volumetric material failure. This corresponds to the yield strength and not the compressive strength of the material. So it's kind of like reducing a boulder to sand in the sense that you can still compress it, but it can no longer sustain any sort of tensile strength. It should be noted that there's also this huge region of extremely low density material that persists in the target. And if you look at the color scale here, this material is of a density of order 1,000th of a gram per cubic centimeter, which for reference is comparable to the density of the air in the room around you. So this material is pulverized into a dusty sort of sand-like material, and this thing will come apart similar to the other one. So to answer the question about whether concentrating the penetrator mass into a single penetrator is more efficient, this will hopefully answer that question for you. So this is the same penetrator mass, 500 kilograms, impacting at 20 kilometers per second on a 50-meter target, but concentrated in a single penetrator. You can see how the persistent fragment is much smaller. We've created kind of a bowl-shaped shell, and the fragment distribution is much more complete. If we take a look at the statistics here, again, we plot the gravitational escape speed here, which is about 3.6 centimeters per second. And you can see how the fragment speed distribution is higher than that. So we've successfully imparted a higher kinetic energy to the fragments. And also the fragment size distribution is much smaller than the original boulder size distribution. But also just in general, qualitatively speaking, this appears to be much more effective, at least for robust disruption. And you can see also how the specific impact energy is higher as well. All right, moving on to even larger impactors. So again, recall we're using this penetrator mass to maximize the payload capacity of a Falcon 9, and we're expanding out to a 100-meter target now. With the original bolide mass being somewhere around 5 times 10 to the 8 kilograms, and the gravitational escape speed being, less than a few centimeters per second, you can see how the average fragment speed is over 250 times the original escape speed. And if you look at the rim of the crater, what is effectively a crater, although the crater is larger than the size of the original target, but the fragments are dissociating off the edge of this crater rim at a speed greater than 60 times the gravitational escape speed. So we can again be pretty confident that with the payload capacity of a Falcon 9, we have a single launcher mitigation solution for asteroids up to 100 meters in diameter, as shown here. So one other thing that we're interested in is studying what happens with sequential penetrators. So this is a high-resolution simulation with a much smaller region showing 2 100-kilogram 10-to-1 aspect ratio tungsten cylinders in a kind of leader-follower configuration. And we're interested in this because we'd like to couple simulations of passive hypervelocity penetrators, as I've shown before, with energy pill simulations, which are meant to simulate the effect of an explosive device, whether conventional or nuclear. And the idea would be that you can deliver an explosive device much further below the surface to utilize its capability as a disruptive device rather than a deflective device. Because if the detonation occurs far below the surface, then you can actually achieve very, very good tamping of the explosion. And a significant amount of the blast yield is coupled into the bulk material of the asteroid. And you can see here how the following penetrator, having to traverse at 20 kilometers per second through this sort of rarefied, high temperature, low density material, and it actually does survive. It should be noted that at 20 kilometers per second, you're arriving at many times the speed of sound in the penetrator material. So as long as the back end of the penetrator can survive all the way up until it needs to deliver the explosive charge, then it won't even know it's really been hit because the shock wave from the initial impact will not have had time to propagate to the back of the target. And similarly, this is a similar simulation showing 5 of the 100 kilogram penetrators, and it's just fun to look at. but it shows how you could potentially deliver with only 500 kilograms of penetrator mass, you could deliver an explosive charge up to 20 meters below the surface of a target. So here we're achieving almost 20 meters of penetration depth. And recall that this is a strength model which is extremely conservative and has boulder strengths upwards of 250, up to 500 megapascals yield strength, which is extremely conservative. So moving on to a 500-meter target, we're expanding out to a 10 metric ton impactor, which exhausts the payload capacity of a SpaceX Falcon Heavy. In this case, I show two plots. I show the material density on the left and the material speed, again in centimeters per microsecond on the right, but I've shown the meter per second conversion for ease of comparison. And because we're ejecting such a significant amount of material off the surface of the asteroid, as you can see here, the momentum enhancement factor, as was discussed in detail by Brent Barbee, is greater than 80. So greater than 80 times the momentum transfer from simply the inelastic collision of the penetrator has been imparted to the bulk mass of the remaining object simply due to the amount of material that's being ejected off of the surface here. And you can see again how the average fragment speed is about 6 meters per second, which is about 30 times the escape speed. So none of these fragments are going to be coming off or going to be returning to the object on a longer timescale. Now, of course, this doesn't achieve robust disruption. We're not going to be completely taking this thing apart, but with such an amazing momentum enhancement factor, this represents a different mode of operation that we like to call enhanced deflection, where you eject a significant fraction of the mass of the asteroid off the surface in order to impart a much larger momentum transfer. Let's see, moving on, and we can also study the fragment statistics of this thing in a similar way as we did before. The gravitational escape speed is about 19 centimeters per second for this object. And again, the fragment speed distribution is shown here in red, which sits entirely above that gravitational escape speed. We have an average fragment speed of about 6 meters per second, average fragment size of about 10 meters, and a total of about 750 fragments at that point after the simulation. This is showing the internal dynamics of what happens inside the asteroid after such an impact. On the left, I show the pressure inside the asteroid, and on the right, I show the material damage parameter, which scales from 0 to 1, where a damage parameter of 0 corresponds to material which has all of its original yield strength, whereas a damage parameter of 1 corresponds to material which can no longer sustain any sort of tensile stress. It can only be compressed. So in red here on the left, I show the compressive pressure, and in blue, I show the tensiles, the rarefaction wave, which follows the compression wave. So you can see there's a series of waves which propagates and refracts the asteroid. And on the right, you can see how the material damage closely follows that initial shock wave. And we actually induce a significant amount of material damage, of material failure within the object. And while we don't achieve robust disruption from this impact, we can be pretty confident from the amount of damaged material that if you were to hit it again with the same impactor mass, you might achieve robust disruption, which is a topic of a simulation that we'll present at a later time, not in this presentation. And finally, the last simulation I'll show here is the largest simulation we've done to date, which is a 1 kilometer rubble pile asteroid with a 100 metric ton single 10:1 aspect ratio tungsten cylinder impactor at 20 kilometers per second. Again, this is not representative of what we call robust disruption, but more representative of enhanced deflection, where we succeed in ejecting a significant amount of material from the asteroid local to the impact site and achieve a momentum enhancement factor greater than 40. The color scale on this plot corresponds to the material speed in centimeters per microsecond again, and we're running all the way out to about 60 seconds after impact. So you can see we achieve we succeed in ejecting a significant fraction of the original bolide mass, and we create a very large crater of many hundreds of meters in diameter. And again, momentum enhancement factor of greater than 40. So I'll let this play out until the end just one more time. And finally, our outlook and future work. We would like to, so the results we've presented today are specific to a very certain type of asteroid, we would like to explore density, porosity, and yield strength parameter sweeps to get a sense of the effectiveness of this mitigation technique for a variety of different asteroid types. And similarly, we would also like to try simulating a variety of different penetrator masses and configurations, in addition to coupling energy pill simulations, which we are actively working on to simulate delivering nuclear explosive devices below the surface. And then finally, one more thing is we would like to discuss with the greater planetary defense community the concept of a counter-rotating terminal guidance demonstration, which is shown in illustration here, where you might launch two CubeSat assets in counter-rotating polar orbits, one which acts as an artificial target, and the other which acts as a terminal guidance vehicle to demonstrate the type of targeting and guidance you would need for order 20 kilometer per second impacts with an asteroid. Obviously, you'd want to do this in such a way that reduces or completely eliminates the production of any sort of fragment cloud in low Earth orbit. And so one potential way you might do this is for the artificial target to consist of a thin film inflatable sphere, kind of similar to the ECHO project, if you're familiar with that, when NASA inflated the thin film mylar balloons as a radio reflector. Or it could just be an electronic trigger where the proximity of the terminal guidance vehicle to the artificial target triggers a proximity sensor. With such a counter-rotating configuration, you could achieve encounter speeds of about 15 kilometers per second, which is within the range of relevance for our simulations. A huge collection of further analytical work, simulations, and other papers are available on our website and on our YouTube channel, which I'll leave these scannable QR codes up for now. And with that, I'll conclude and I'll open up for questions. Thank you.
Thank you very much. This is amazing work in the context of last minute counter asteroid, right? That's something you can launch from the ground and essentially minutes before impact, try to save a key location on the surface of the Earth.
Right.
We do have a question from Ken here.
So this simulation, do you consider the rotation and the high speed in space? So some asteroids moving, rotating, and moving very high speed. That's number one. Number two is how is it easy for Falcon Heavy to align for head-on impact in front of the asteroid or behind the asteroid or from the side of asteroid? So you consider this simulation effect, how effective in those situations compared with your simulation you showed today?
Yeah, absolutely. So to answer your first question regarding asteroid rotations, it's certainly an interesting question. We have not explored that in our simulations. It should be noted that at least for rubble pile type asteroids of the type that I'm simulating here, the expected rotation rates are not extremely high. Of order, the maximum rotation rate is about 2 hours per rotation. There's actually some very interesting work done in this area, which was actually presented in one of the talks earlier regarding asteroid rotation rates and how the average strength of asteroids can be estimated from the rotation rates. But no, we have not simulated the effect of asteroid rotation. It's a very interesting point. Regarding your second question and getting your impactor out to the asteroid, what's interesting about energy transfer rather than momentum transfer is the asteroid is coming at you in the reference frame of the Earth with all of the kinetic energy it needs to disrupt itself. So really all you're doing is getting in front of it with your impactor array. So the mission design space is actually a lot more versatile in that mode because you're not having to go out and hit the asteroid with all of the speed that you can get from your launcher per se, but rather you can just get up in front of it and let it run into you, which is a much simpler configuration. I hope that answered your question.
But how easy is it to have a perfect alignment?
So I guess the question is, simulations show that you hit the asteroid head on. What happens if you hit the asteroid from the side, which is a more typical way of intercepting those objects, right? It's very, very challenging to intercept those asteroids or a randomly approaching asteroid head on, right, from a random location, right? That's a basically the question, I think.
Yeah, absolutely. And part of the parameter space we would like to explore in future simulations, we've kept it pretty simple in these preliminary simulations, is exactly that, exploring off-axis impacts, exploring impacts that are at angles relative to the asteroid velocity vector, and also exploring impacts where the axis of symmetry of the penetrator is at an angle relative to its velocity vector, so it's not coming in directly perpendicular to the surface. So all of these asymmetries and misalignment cases are part of the parameter sweep that we will be doing as the simulation campaign goes on.
Yeah, excellent. And also probably off center of gravity collisions with the asteroid, where you might break part of it, not everything, which is probably a more typical likelihood than hitting the CG of an asteroid. So yeah, very cool. Any other questions, Mark?
I got a couple. The first, I thought it was really good work and a good presentation. Thank you. And I had a couple of questions. One was, for planetary impacts, there's been some suggestion that there's an antipodal stress concentration, and there would be eruptions of lava, like the Deccan traps being antipodal, more or less, to the Chicxulub crater. So there might be an outflow of basalt, but I wonder, do you have any concentration or spallation of the other side of the sphere when you do these? In one of those, I could see the shock waves coalesce in the other point and then reflect back. Yeah.
That's exactly right. It's a very, very good observation. And actually what we suspect is that this is a product of using a perfectly spherical target, and that we will not see such focusing of the shockwave when we use actual asteroid shape models that are more multi-lobed and aspherical. So, yeah.
Sure. Okay. So I have another comment here that, as a geoscientist of sorts, I have an interest in what's inside these things, and in particular, if they're formed by a disruption of some other differentiated planetary body. Are there any chunks left that are large pieces, including like core mantle boundary or things like that? So I'm mostly, that would be the most interesting thing to see is what is the what do the innards of a planet look like, and yet it's not really. It's probably a rubble pile, but some chunks within the rubble pile are big chunks, and there might even be something like bedrock. So this kind of impact, if you were to try it out on some asteroid out there, you might be left with the big stuff left in the middle that then you could finally see. And that could be of some scientific interest to get rid of all the regolith and see what are the innards of this body like.
Absolutely, I completely agree. Yep.
Any question online or from the audience? So please come along. One more question for you, Sasha.
Hi, Sasha. Great presentation. I'm sure those dynamics and the computations are very intensive, so it must take hours and hours to run. But my question was, it seems like you're assuming some sort of distribution of the material and the density within your asteroid there. So my question is, what are the kinds of assumptions you're making for the distribution of the various density and set materials? Are you running some sort of Monte Carlo simulation with varying density, material properties, and especially distribution? Especially if the assumption is there's a core center of like large density material that's surrounded by lower density particulate matter, and how would this huge variability in the density of your materials cause like different impacts in terms of the escape velocities and the overall trajectory?
Yeah, absolutely. It's a very good question. So really, because we don't know what the internal structure of these rubble pile asteroids really is, it's a little bit of a shot in the dark as to estimating what the internal structure is like. Hence why we use such a conservative material strength model, because we really don't know what the strength of these boulders will be. So to answer your question bluntly, it's our best guess. for these preliminary simulations. We use a boulder size distribution, which is a power law, which is, I can't recall, someone brought up the comment about how these rubble pile asteroids are likely the result of prior impact and disruptive events from asteroids on asteroids. So it's likely that the boulder size distribution inside of these objects is similar to the size distribution you would expect post-impact from, the size distribution of ejecta from an asteroid on an asteroid impact. So that sort of informs the size distribution. Obviously, we can't simulate boulders below a certain size scale because we're limited by our mesh resolution. And so below a certain size scale, the material is assumed to be continuous. However, the simulation of other types of asteroids that are perhaps stronger or perhaps weaker or perhaps filled with voids or comprised of multiple different lobes is left for our future work. And that we're excited to explore those parameter spaces, but have not done so yet.
Thank you, Sasha. Regarding counter-rotating space demo, maybe get in contact with me and see if we can talk more about it.
Absolutely. I look forward to that. Thank you.
Thank you, Sasha. And I think now we're going to move to the last talk of the day, which is by Brin, I believe, on a similar topic, except he's going to look at the ground effects, right? So, Brin, are you online?
Yes, can you hear me?
Yes, we can hear you very well. And let's see, do you have something to share? Oh, yeah, now we see you.
Okay, perfect.
Excellent. So please introduce yourself, and the floor is yours.
Sure, yeah, let me pull up my presentation quickly. Okay, can you all see it okay?
Yes, we can see very well.
Okay, perfect. Yeah, hi everyone. My name is Brin Bailey, and much like my colleague Sasha, I'm an assistant specialist researcher in Dr. Lubin's group, the Experimental Cosmology group at the University of California, Santa Barbara. Thank you so much for giving me the opportunity to further our discussion on PI, our multimodal planetary defense study. And whereas Sasha focuses on the intercept side of things, as he mentioned, my main focus in our group has been on what happens after threat interception, focusing on what the consequences are of disrupting an asteroid near Earth and how that might affect people or infrastructure on the ground. So although we've been hearing about it for most of the day, I'll start by giving a brief introduction to planetary defense as a whole, just to make sure we're all on the same page before narrowing my focus on PI. Coming off of Sasha's talk, I'll describe a little bit how PI works, but particularly in threat scenarios where there's little warning time before impact. I'll then go into a bit more detail on the consequences of these short warning mitigation scenarios in order to introduce our ground effect simulations. And finally, I'll discuss the results of these simulations and what their implications are. So to start things off, let's talk about planetary defense. Definitely some of this might be a bit repetitive by now, so I'll go through it quickly, but I think it's just important to set the stage. So as others have discussed today, the core of planetary defense is the effort of monitoring and protecting Earth from incoming asteroids. Space debris entering Earth's atmosphere is not uncommon and usually consists of small bodies or fragments of bodies that are not considered threats. But on occasion, we may be visited by larger objects that do have the capacity to enact damage. So what does planetary defense traditionally look like? Well, as Brent Barbee discussed in his really great talk earlier, the tried and true method for mitigation is deflection, the idea of changing an asteroid's motion in space through kinetic impact, like we saw with DART. So DART showed us that we can use deflection to push something out of Earth's path if necessary. But a deflection mission hinges on a few key parameters. So first, we have to see the asteroid coming, and this has to give us enough time to design and launch a mission to deflect it relatively far ahead of its impact time so that it's far away from Earth, which is on the scale of years, if not decades. So why do we care about planetary defense in general or about finding new ways to do it? Well, as I mentioned, while most near-Earth asteroids are small and non-threatening, there's always some possibility that something bigger could come by or that we don't see an object far enough ahead of time. So as several others have mentioned today, just want to briefly talk about Chelyabinsk. The Chelyabinsk asteroid airburst in 2013 is about an 18-meter diameter asteroid with an estimated impact energy equivalent of between 400 to 600 kilotons of TNT equivalent, which was about 25 times the yield of the Trinity test, or about 20 to 40 times that of the Hiroshima blast. The airburst caused damage out to 120 kilometers from the supersonic path. Glass was shattered and broken in more than 3,600 apartment and commercial buildings. People sustained over 1,000 injuries. And to put it into perspective, objects at least the size of the Chelyabinsk asteroid are expected to impact Earth about every 50 to 100 years. Now, slightly larger than this was the Tunguska impact in 1908, with an estimated about 40 to 50 meter diameter body, with an estimated impact energy between 3 to 15 megatons. Now, this is a really wide range. Obviously, ranges by an order of magnitude. That's because the data is pretty uncertain. It's really fuzzy, and there's certainly arguments to be had on both sides of the spectrum. But in any case, this resulted in a butterfly-shaped area of destruction, spanning about 2,000 square kilometers. The resultant shockwave flattened a large portion of the surrounding forest, potentially on the scale of millions of trees. For objects similar to Tunguska, these are expected to impact Earth between every 300 to 1,800 years. Again, this is a really wide range related to that, wide uncertainty in impact energy. But in any case, current planetary defense strategies are not well equipped to combat a wide range of threat scenarios, particularly in this short warning regime where there is little to no time before impact. Now, as planetary defense has really grown in the last several decades, there's been a huge focus on detection efforts, and this is great because you cannot deflect what you don't see coming. But since planetary defense is about monitoring and protecting Earth, why not expand our mitigation efforts as well? So to achieve an extensive planetary defense system, it's imperative that we are prepared for a wide variety of threat scenarios that considers a large range of threat sizes and warning times. And so we argue that such a system should be comprised of a layered structure of reliable methods for both detection and mitigation efforts that can help to prepare us for anything. So that really kind of begs the question of, can we append existing planetary defense technologies with a new approach that can provide reasonable mitigation of short warning threats? And if so, what are the potential effects that this might have on humans and infrastructure? So again, we propose PI, not to replace any existing planetary defense method, but as a supplementary approach to bolster our response to potential threats. Now, rather than using momentum transfer as in deflection, as Sasha mentioned, PI works by imparting energy transfer to a threat. And as Sasha previously described at length, PI's approach in essence is to penetrate an incoming asteroid with high-density, hypervelocity impactors, which would enter it and break it apart into many small fragments. So this represents a versatile, multimodal approach that could be used in a wide variety of scenarios, whether the warning time is on a scale of days or years, or for asteroids the same size as Chelyabinsk or as Apophis. So in longer warning scenarios, where an impact is months or years away, the fragments can miss Earth entirely, which completely removes the threat. Now, depending on an asteroid's size and speed, a short warning mitigation scenario could be feasible. So in these short timescale intercept scenarios, which we refer to as terminal scenarios, the fragment cloud would enter Earth's atmosphere, where it would disperse the energy of the original asteroid. Now, we do really want to stress, however, that PI's preferred mode of operation is in the extended intercept regime, where we could intercept an asteroid far ahead of its impact time in order to keep the action away from Earth, because it's always preferable for any method of planetary defense to be used far ahead of time and as early as possible. And additionally, I should note that as our detection efforts increase from systems and missions like the Rubin Observatory's LSST and NASA's upcoming NEO Surveyor, our situational awareness will really improve. And this means that we'll be detecting more NEOs and more potential threats, thus hopefully decreasing the possibility of short warning to no warning impacts. But of course, before we get to this stage, and even after we do, it's important that we remain vigilant because it still remains possible that we might miss threats like these, particularly if they're coming from the direction of the sun. And in any case, our findings do suggest that PI is uniquely capable of operating in a terminal mode in certain scenarios where the factors are favorable. And as terminal scenarios are really the only scenarios where we would experience the ground effects, I'll be focusing on use of PI in its terminal mode in this talk. Though, again, I do stress that we don't want to use this unless absolutely necessary. So this hypothetical represents a sort of worst case scenario. So in the terminal mode, during atmospheric entry of the fragments following fragmentation, The pressure exerted by the atmosphere will eventually exceed the fragment's material strength, causing a cascading breakup event. And as pressure and heat increase, the fragment will ablate and the material will fail, causing the fragment to detonate or to burst. Now, collectively, these bursts produce optical flashes and decorrelated shock waves on the ground. These optical and acoustical ground effects spatially and temporally distribute the energy of the original asteroid, which in reasonable mitigation scenarios that are appropriate for the threat, result in little to no damage. Okay, so how do we simulate the ground effects? Well, we have a suite of custom codes that have been written by UCSB students and employees like myself over the past few years for both the optical and acoustic ground effects. So first, we design a given mitigation scenario based on threat size, speed, and average density, among other parameters. We then decide how many fragments to break the asteroid into, which will, of course, determine the average size of each fragment. And to simulate the uncertainty in a real mitigation case, we introduce statistical variations to several fragment parameters, such as diameter, density, yield strength, burst location, and the velocity at which fragments move away from the cloud center of mass. We then calculate the position and burst height for each fragment and ensure two things. One, the fragments burst at reasonably high altitudes, and two, the ground effects are not too high. So we set damage thresholds for the ground effects to ensure that any potential damage is minimized. So for the optical effects, we want to make sure that the cumulative optical energy deposition is